Nice. Well, I just went ahead and kicked my stream off. We can
I'm on my 4th intro song.
chill out and wait for Alan's intro to run here. Everyone, thank you for being here. We'll hold on for just a second, and then we'll do a proper intro once Alan's intro is done. Intro song.
Oh, I remembered to hit Rockfin Go. That's excellent.
Nice. Does it just not work if you don't do that, or?
You have to separately hit Go every time, and I remember half the time.
Ooh, yeah, that's rough.
Only for Rockfin Needles.
All right, Toby, we're live.
Hello, everybody. Welcome to Æther Roundtable number 33. Tonight, we are going to talk about cartography, well, as you see here on the screen, cartography, projected coordinate system, and cosmography. So Shane is going to go ahead and ladle this gravy for us. So yeah, thanks for being here. Shane, whenever you're ready, go ahead and take it away, my man.
Right. Thanks to excellent opening. Each time you do them, they get better, I think. That's excellent trend. Let me make sure my stream is not muted. One audio, desktop. Yeah, all right. If my stream sucks, somebody tell Alan, and Alan will tell me. All right. Looks like a good Canvas open in Discord. So this presentation is like something I've been piecemeal building a little bit all the way through, and then recently revamped up because everybody makes the same misunderstood points over and over, and then make permutations of these misunderstood points. And before you know it, there's a whole series of arguments that are based in like ridiculous retardation. Okay. So let's go with the map question. We're going to start with cartography. We're going to go into, let's see, I got the itinerary. That's how you know I'm prepared. All right, so we got 120 canvas slides. It's going to be real quick. I think about 90 minutes, right? We're going to do map projections, projected coordinate systems, types of projections, get that knocked out. Everyone always likes to jump in and demonstrate how they know everything is from a sphere going to a plane, and that's why it causes all the world's problems. We're going to nip that in the bud right away. And then we're going to go into AE map, specifically distance, equidistant, Haversine, cosine law, great arcs, and linear meridians. We're going to go into celestial curvature, where that comes from, how we derive that, every which way, and which coordinate systems we depend on to do that. Ending with the astrogeodetics, the combination of the cartographical and the celestial, which has absolutely been done one for one. It's how things work the way they do. And then comparing sphere to hemisphere, the geocentric, heliocentric perspective comparison, or the 3959 radius on a flat Earth versus the globe Earth as is comparison. Yeah, hint, they're identical, but they won't say that. And then we'll top it off with the cosmography, the topic that used to be all of this, but never, there's now a historical footnote, and they've divided it to, of course, geography, cartography, hydrography, and all the different ographies that would all have been comprised in cosmography. This is definitely related, but I think it was our boy Zetetic has an archive of things that are incredible mine, and this is one that kind of made it in there. There is epic music playing, but you guys can't hear it. All right. Am I sharing sound? Do you guys have sound? I don't think Canva's going to share sound.
Yeah, I don't think we're hearing. Well, I did hear.
If you share it through your browser, it would.
We heard the video. We heard the music for the video.
You did? Okay.
Yes.
So then,
when you think of the world, this
Yep.
All right, cool. This is like the main dude who does like the basic mainstream surface level analysis on this. Like if anyone doesn't know this and goes on the internet tomorrow, this will be all of their conclusions. So we'll just start there. It's like
is
2 minutes.
probably the map that comes to mind. It's everywhere. Atlases, school walls, even Google Maps. It's also very, very wrong, and it's been distorting our view of the world for centuries. This is a Mercator projection. It's one of the most common projections used for world maps. This guy, Gerardus Mercator, created it in 1569 to help with ship navigation. The map was revolutionary because it straightened both lines of latitude and longitude, which was great for sailing. All you had to do was draw a line to where you wanted to go on the map and follow your compass. But to make a navigation-friendly map, the projection distorts landmasses the closer they are to the poles. That gives us the wrong idea about the relative size and maybe even the importance of some regions. This creates what some map makers call the Greenland problem. This is Greenland on Mercator's map. It's huge. Here, Greenland is bigger than the entire continent of South America. The same thing happens with Alaska. The state looks bigger than the entire country of Mexico. The farther land is from the equator on a Mercator map, the more stretched out it looks. In reality, South America is 8 times the size of Greenland, and Mexico is actually bigger than Alaska. For the same reason, this is what 2,000 miles looks like on a Mercator map, but so is this. It's the same distance, the fault is in the map. This happens because map makers have to rely on mathematical formulas to project the surface of the Earth, a sphere, onto the surface of a map, a plane.
No, that's where we're going to stop right there, because that's where everyone concludes, right? Obviously, it must be that the globe is the real map and can't be distorted, and we got to project it onto these pieces of paper that are stubbornly planar and can't do the globe justice of the curvature, right? That's what everyone says, man. No, like not the case. Let's start here. So Wikipedia, the king of mainstream nonsense. Do all maps simply project the globe? No, they project what? Coordinate systems, or in this case, projected coordinate systems specifically, right? So all projections of a sphere on a plane necessarily distort the surface in some way. So everyone includes this all the time. Every chat GPT will also answer your question, probably after lying to you, and then give you this. But it can't be because of this. Interestingly, there's 4 or 5 of these specific points that I think mainstream only argues because of us. And you'll know them, I think, when you hear them. So there's really no other need for them to have the argument, except that we brought up the counter. So what maps project are coordinate systems. And overwhelmingly, in this case, would be the geographic coordinate system, the longitude, latitude grid that we all know and love, also known as the graticule, is the necessitated curved model from converging longitude lines that derived from the celestial sphere and angles to the stars, gives us the pseudoscientific, not real globe Earth. So, let's see here. The other coordinate systems that you could use that wouldn't unnecessarily add sphericity and do all sorts of crazy things would be anything like the universal transverse Mercator. We'll go over that and the Mercator a little bit later. Local maps actually don't give a shit about any of this. They use their own state plane coordinate system. And my state mass has, I think, 2 separate ones, and you can just do that, and then nobody pays attention. So how they instilled us with the longitude latitude system is really easy to see. No one gave a crap. The Cartesian coordinate system you can always use to project. That's just number lines, essentially, like X, Y, Z. You can do a number line in dimensions, and then that gives you your basic Cartesian coordinate. Nothing wrong with that. It's a good representation. We'll be dealing with it a bunch later. And then you have, of course, our favorite satellite, Geocentric, Geodesic, Earth-centered, Earth-fixed, and ECI coordinate systems. Point is, there are a bunch of coordinate systems, and about 75% of them are based on angles to the stars, are inherently spherical. So even Wikipedia will tell you, hey, your map is projecting a coordinate system, and then it will also give you the pseudoscientific, but all the projections are spheres, and spheres are best in spheres, but planes, etc. The same thing. But really, a coordinate system is just based on a datum, right? Everyone who does surveying knows that. A datum is what ties it to reality. A datum is the basis of everything. And in this case, the datum would be something like the celestial sphere, an observation to a longitude, latitude line, an elevation of Polaris, equinox for the longitude, etc., etc. So they give us a little bit of fake history there, but we'll go into that when we tie it to longitude. Right, based on a datum. So coordinate system without any datum is just numbers in meaningless space, kind of like space-time continuum, relativity, for the space-time fourth dimension of nonsensical bullshit, all that stuff. coordinate conversion, of course, we'll get into that, but this one says that because you have a system, you can convert to other systems, and that's actually inherent in all systems, and you can convert within a system and to other systems seamlessly and with various effects that get skewed. So this, of course, geographic, right? Inherently spherical. It's identified as a spherical coordinate system. So when we're using longitude and latitude, and we're like, hey, does that converge? Will it match the globe? Will that distance be a geodesic? Will it? Yes. Yes to all of that every single time, always and forever, because anything using this system will output, input, and deal with the system's data variables and offsets. A good way to think about it is if you use half the sphere and then you do some, let's say, co-altitude angles or an adjustment to a right ascension on 90-degree offset or a good 90 radians adjustment, whatever, you're using the opposite half, which would be like the antipodal to your non-existent sphere. If you have a hemisphere, right, you're assuming there's a sphere below you, you can do math based on that and it works perfectly. That's how the celestial sphere is born. That's how people get confused, but we're going to equate that also near, I think, the middle of this. So the geographic coordinate system, longitude, latitude, is not a projection. It's not a aspect. It is the framework, which is then projected into every available map projection. 201 ways to look at this curved data. You can have any which way you like. You take your pick. Freedom, right? There are other coordinate systems. This is the one we use. This is the one we're allowed. This is the one they lied about. This is the one with the Wikipedia history and the Longitude Act from the one dump from that one museum in 2014 from our friends at the Royal Society. There's a whole nother presentation on that, but we'll be summarizing it, I think, pretty quickly. Right, so when we have a referencing system, again, inherently spherical, longitude and latitude, because they're by their very nature, right, they're going to necessitate other spherical components, namely great circles, great meridians, arcs, bisecting, essentially everything that you would assume from a actual sphere, except, there is no actual sphere. This is all made up based on angles to the stars, with them filling in the blanks with math, right? So again, even this presentation is like, listen, when you put a sphere, a perfectly excellent, divine, nothing wrong with the spherical thing, onto a planar, crappy map, you have all these things that'll never be good enough, and it's always wrong in some way. And it's, well, while that may be the case, geometrically and plausibly, that's not because Earth is glob or sphere. It's because the only coordinate system anyone has ever used, longitude, latitude. How do we determine latitude? Well, you look up at the sky, you decide which in your spherical, hemispherical view, what inclination and great arc circle it's doing, and you say that is its elevation, and you're like, oh, look, lo and behold, that's my latitude. And you're like, great. With that, you can actually navigate pretty well everywhere, right? You can do that. You can get the equinox. You can get a longitude, a perpendicular derivative. You can coordinate anywhere you want to go. Use the stars. Use the clock stars in the middle. You can use lunar transit. You can look at Jupiter's moons. They had methods that got them to within a half a degree anywhere they wanted to go. No big deal. So nobody needed coordinated geographic coordinate systems derived from the stars to be inherently spherical. Nobody needed this, right? And if you look into it, you'll say, actually, we've always had that. We've never not had that, which obviously is wrong, but we'll get to that. So the new term that everyone will be saying, I think, after this, I've been trying to say it a lot, the graticule, the gridded network of lat long, the spherical baseline infrastructure from map conversions, flight path arguments, distance misunderstandings. What else do we have? Oh, obviously the shape of a continent in the south. Obviously, this is, because of the graticule. It's all based on the graticule. Every map projects coordinate systems. The coordinate system of longitude and latitude is a geographic one, also known as the graticule. Everyone's with me, right? You can definitely stop me, chime in, throw some shit in, whatever you guys have questions too. Pretty open-ended.
You have my gratitude for the graticule.
Nice. First quip. I like it. Also, why are you at 10% volume?
I don't know.
Okay, you're up now. I had you at 69. I can almost hear you. Let's see. So, graticule projected. This is, again, the spherical object that we're putting into map projections. Is not the de facto proved verified globe that we said it is. It's the basis for the globe. the celestial sphere based coordinate system that we then use for maps. So we can do, this projection, a cylindrical, a conical, we can do equal area, we can do all sorts of warpings of our beautiful, perfect spherical shape. That one's for later, so we'll get into that one. Again, the graticule, right? The map projections on various distortions and projections. You can look at it any which way, always knowing that it is the graticule, except when it's the azimuthal, and then you can make up stuff like it's actual. And it's the only map that can't do a bunch of stuff. The only map that can do stuff. It's really weird, especially considering it's part of a group of maps that none of the other ones have the same apparent effects as this one, but only to the online community. So we'll sort that out. This is from one of the papers that I read to go over to this. By the way, there's like 7 or 8 papers referenced in the back. There's the whole presentation slide deck, the resources, the links, all the coordinate systems, everything, of course, is in the database. So I have a whole host of links I'll drop later. There's also file share for all of the material that we're looking at now. This is just a page. Oh, wait. Discord push to talk has to go off. Hey, there we go. All right. So here's a page for, doing a particular coordinate transformation. It's projecting it out. It's doing a whole bunch of trigs, some math, and some calculations to determine how the sphere will be corrupted in this particular projection. Whenever you're doing math based on, say, radians, sine, cosine, trig based on latitude, longitude, you're starting in the system of geodesic, the spherical geographic coordinate. You're doing it in there, and you're going to end up in there. There's no way in the world that your math will conclude anything except that the coordinate system you started with is in fact verified when you're done. That's just the way it works. So all maps are just projecting our boy the graticule here. Here's a bunch of spinning globes with some grids. Yeah. So one of the properties that are inherently spherical that it forces on all its projections is bisecting meridians. You can cut a sphere in half, you get 2 equal sides. That makes exactly one biggest circle. Right? We have the globe has an equator. That is the great circle or prime meridian or whatever you want to call it. Every other circle is a small circle on the globe, and that circle is the biggest. Obviously, that wouldn't be the case for a flat circular Earth with ever increasing concentric circles that get progressively bigger. But for the interim, right, we only have one coordinate system that is based on these longitude lines that theoretically and metaphorically, pseudoscientifically do converge, and that's what everything is based on. That's what everything is tied to. That's what everything will equate to. As I just said, from the coordinate system that we're in, we'll always prove and work with the coordinate system that you're in. So this is quickly from the sky mile presentation. So we're going to fly through this real quick. Greater and smaller circles are inherently spherical. They are things required by a sphere, not a circle. Their existence actually is necessitated as a sphere. And if you look through the Wikipedia history of the revised area, everyone was all about great meridians all through sailing history. Everyone was always trying to measure the longitude and the great lines, except they did it with rhumb lines and planar surveying and straight lines until the globe was like, well, no, that circle is actually on the globe, even though it's exactly the same. And the inner circle here, the circle that you're on, is on the globe. And then they kind of changed the whole navigation system. It wasn't a circle, it was a spiral. And then we had, longitude, the whole inserted history. Going back to greater and smaller circles, this is just real quick. One bigger circle, every other circle is small circles. So it is, like I said, inherently spherical is the characteristic we're going to take away. Every great circle is the intersection of the sphere with the plane. That is actually super important. When does a timer go away? Yeah. It's super important to have a great, what did I just say? Right, the intersection of a spherical plane, that right there is the basis of like a geocentric coordinate system, the basis of a horizon-based coordinate system. If you can't divide it in by a mid area or a baseline, then you can't do anything off the baseline, or you can't do anything. You have to have a way to do that. The horizon works for a great many of them. And in this case, if you have a sphere, you start by dividing that sucker in half, and then you can build your coordinate system from that. That's, again, why longitude in the Great Prime Meridian was so important, for them to be able to choose where the circle began. right? Everyone knows that it's a circle and it doesn't really have a beginning, except for the Royal Society, and you can literally make it so and choose the beginning. But so a meridian line is longitude running from the north to the south. That's just what we have longitude. They just arbitrarily decided that they would start at the zero at the Greenwich at the Royal Observatory that they built 300 years ahead of time for other non-related celestially observing reasons, or exactly all the same reasons maybe. But anyway, they chose the zero, and that's what determined the start of the circle. And before that, nobody could use the circle because nobody knew where it started. Obviously, that's retarded. Everybody was choosing a circle and then denoting the correct increment using, say, time, 15 degrees per hour, and what ended up being the Great Ascension, right? The rate at which the stars turn forms the unit of measurement by which you gauge it. So that's how they did it. That's where they started. We're going to start in the same spot. This cursor is always on my other screen.
The complementary angle of declination is called the pole.
So this is a quick, I think it's 2 minutes from this dude. It's a really awesome video. We're just going to use a snippet. He goes into, I think, great circles and how a great circle on a plane in your hemispherical view will do a very good job of convincing you that you're living on a spherical Earth.
Polar angle. It is represented by the interior angle of the cones and is used when converting between coordinate systems. The polar angle is measured relative to...
Right there. So he goes so quick and he's so dense. So coordinate system. This is the spherical trigonometry inherent in celestial navigation. It's not directly. You're not actually computing it. You're depending on it to convert between coordinate systems. In particular, right ascension, declination, and longitude. You're converting a sub-angle or the bottom half of your celestial sphere. You're using that corresponding co-altitude angle to get a measurement on a conversion to radians and time. So it's essentially taking 15 degrees per hour and making it the equivalent in the right ascension declination coordinate system as it would in the geographic. And perfect. So this dude just said like 7 words and it was pretty well described, pretty simple.
To the plane of the poles to the cone's edge and is therefore equal to 90 minus the declination of any given cone. Since the celestial equator has a declination of 0, it's a great circle. Every other declination is represented by a minor circle with an apparent radius based on its angular position relative to the equators or poles. Basically, the apparent path of a star of a specific declination is determined by the angular distance of the declination from the equator. It also determines the angular radius of the circular path of the object as it completes a rotation around the axis of the poles. Here's an example of how the declination coordinate would appear to you if it were traced in the sky. The layout of the system in this example is based on my location in Florida at a latitude of about 27.
He's got North Celestial Pole marked there. He's got the South Celestial Pole. He's got his little acronym, but that's what that means.
3 degrees north. So we can see that the NCP is located at an altitude equal to that latitude. The declination coordinates are the circles radiating out from the NCP, just like the circles created by the cones representing declination on the example sphere. As time passes, watch how the stars stay fixed in their position relative to the circles of declination. This is why equatorial mounts are useful for long exposures. Since the declination of an object is constant, the mount only has to slew in one direction to compensate for the Earth's rotation.
And again, real quick, the equatorial mounts just means that it's assuming this motion continues when you can't see it through your feet through a same size circle as it would if it went around the circle of the Earth, set when it left you, and then rose when it came back around. Those two things are equivalent because it's the same size circle based on the circumference, which again applies to a circle as well as a sphere, but is always misinterpreted spherically.
Rotation. Here's another view from the same latitude, this time looking west. We can see the celestial equator is separated from the prime vertical at an angle equal to the latitude, which is also equal to the altitude of the NCP.
Right, so coordinate system based on the stars, literally 1 for 1. Elevation angle of this star equals latitude, 1/2 of my grid system. Super easy.
Declination coordinates in this view are the lines which are parallel to the equator. From this viewpoint, you'll notice that the declinations closer to the celestial equator have apparent angular radii which are much larger compared to the ones near the NCP. This is why they appear to be arcs when in fact they are actually circles like in the example sphere we saw earlier. Watch as time passes here, and again you'll see that the star's positions stay fixed relative to the declination circles. For a given interval of time,
the celestial equator is just the actual, like a mere representation of the actual equator. It's the universal comparison mark, so it's not personal. Like you don't have your equator and my equator. the point of the azimuth alt horizon grid is that I can point to where it is for me, but I can't convey to you where it is on your grid without a medium ground. And this would be the actual way that you do that. Use a celestial horizon that everyone can base their coordinate system on. And that's how you convey the location of anything in the sky to anyone.
The stars with declinations closer to the celestial equator appear to move faster than those closer to the poles. This is due to the fact that the apparent angular radius of the paths of stars closer to the equator is larger. The difference in the apparent speeds of stars due to Earth's rotation is referred to as apparent angular velocity. The apparent angular velocity of a star is dependent upon the declination of the given star, and is measured relative to the observer at the center of the sphere in terms of horizontal coordinates. Here's an example of the difference of apparent angular velocity of objects located at different latitudes of a sphere. Any given angle labeled theta.
Man, he goes so like uniform and just this. It's all gravy. He's just like data information, excellent. But back to our projections of the coordinate system that's already spherical. How and what ways can we distort, corrupt, destroy, and not actually do the sphere that is divine and perfect justice? Right? We have the cylindrical distortion, conical, planar. We can preserve 2 out of 3 aspects, but never all 3, right? If we're projecting our beautiful sphere, we can do so in any number of ways, but inherently we'll never preserve every aspect of that sphere, right? So most projections are what they call tangent projections, where they take the sphere and they address it from a point or a slice or a specific perspective, and then from that position they preserve, say, the axis or direction or a distance or 1 or 2 of those, and then they sacrifice the other one typically. But again, we're trying to geometrically we're kind of force the square into the circle peg in preschool, and the teacher isn't stopping us, right? We're just gonna content to let us keep doing that. So cylindrical projection, as we started with, of course, has the north and south totally skewed with the big Greenland, and everything looks like it's huge. But of course, if you take a sphere, roll it into a cylinder, you sacrifice the poles, you preserve equidistant stuff in the middle, mostly for everyone, right? Don't worry about the poles. Here's how you can navigate, get your ruler out, essentially. Oh, but by the way, does anyone know if anyone has used a ruler to try and gauge distance on the Gleason's map? Has anyone seen anyone try that?
Yeah, there's a guy on Rockfin
A ruler.
On what's his name's video.
So like he takes a point
Okay.
on and he marks like a linear point, and then he says that that's all one direction.
I can't recall, but I think so. Something like that. He does like several iterations of it.
Gotcha.
I
'Cause
recall.
people were like, "Oh, they use a ruler," and I'm like, I don't understand why. If it's preserving the directions as an inherent aspect, and then you're shitting on that and then deciding that you're going to take that and go the other direction, which of course is wrong and skewed. And it's like, oh well, you should choose a different projection if you're just going to fuck with all the directions, right? The circle on the AE map has to keep correcting to go east and west, right? The circles, you can't draw a straight line anywhere to do anything without correcting. That's not how it works. You've ruined the only 2 of the only good things about the projection that you chose to use. So crazy. But you can do that on things like the Mercator, equal area cylindrical, and things that preserve, say, the middle, or preserve that aspect, and then sacrifice the poles or the cone, as this conical would, right? So it says producing. We can't ever reproduce the sphere perfectly because science, and sure, Egyptian gods and the sun worshiper. I'm sorry, science probably. So we can distort the globe in all these ways. We can do conical, cylindrical, equal area, equal distance, direction. We can preserve all or some of these, but never all of them, right? So here's all the basic ones. Cylindrical, transverse, oblique cylindrical, conical, spherical. They're all types of secant. And then here's the great amalgamation slide of all the different ways we can't quite reproduce the perfect sphere plane on the perfect sphere on a plane. Cool. Moving right along. We have the basic family of projections, of which the categories you'll see are many different projections, and then the basic aspects they preserve and lose according to each category. So you get cylindrical, which are, again, wrapping a cylinder around the Earth. You have the Mercator, transverse Mercator, Miller cylindrical are all types. Conic, which is projected on the conical surface, and it would do, say, like conformal conic and as equal area. So you have equal area measurements. Is my dog just gonna keep whining at me? He is. All right, bud.
Give him a couple gradules or whatever.
He doesn't like graticules, but he does like treats. 1 second.
Give that dog a couple graticules.
Brand new bone. Saved it. Clutch. All right. Did I finish that? No, I didn't. But we're getting it. Azimuthal is a type of projection that preserves, say, directions from a center point and equidistantly. So you can measure distances from the base coordinate system, not only from the north along the line of longitude, but also from any geographic coordinate point to any other geographic coordinate point, as you can with any projection that's projecting the geographic long lat system. There's no type of map that you can't do that on. Only confused people on the internet say that. Back to our distortions of a perfect divine sphere. And again, the equatorial, transverse, oblique, all the basic types and projections. We do have a program called Projector that we're going to get a random map off the internet and project it into any type you guys want to see, and we'll show you how that works exactly. Oh, Eva. Okay, dude. So let's start with shape. Right. So we want to keep the shape. We can do, say, the size of Australia. We can do a ratio of the size of Australia. We can project it. We can preserve it. We can distort it at the expense of everything else. You can sort of pick your poison, right? So we have basically these: equidistant, conformal, equal area, and azimuthal, right? And then you have a compromise, which is a little bit of each, as you might expect. We're just gonna sail through here because we're going to deal with the coordinate systems that inherently inflict sphericity more than these map projections, which are all identically projecting the same coordinate system. And again, longitude, latitude is the system. It is one of the only systems we use. It's Google Earth. It's WGS84. It's every satellite. It's pretty much the Earth center, Earth fixed. It's the basic celestial sphere on the geoidal Earth. It's 90% of what we do base things on, compare things to, and also judge things by. So basic equal area, it's what you're looking at. That's what would preserve, say the distance between the continents. But again, if you look at the longitude latitude line, any point to any other point, you would do some math, get some cosine, do some trig, backwards compute the exact distance based on that starting coordinate system or the longitude latitude sphere, and boom, get the exact answer, which I would call globe distance or the curve distance or the geodesic arc to the actual linear line, the chord to the arc. You guys get what I'm saying here. Although I did, when I was arguing with Omnivore, he said when I go fast, he's like, "Oh, I stopped listening to all of that, and you're gish galloping, even though you didn't stutter, and all of that was on point and relevant. I didn't hear any of it." And I was like, "You might not be alone in that, so I should probably not do that." We're going to do a whole section on the AE specifically and how that works and what it can and can't do. So we're going to pass through that. This is, again, a true direction projection is an aspect you're going to save. And then if you take a ruler out and start measuring stuff, you've ruined that one thing that you saved. So I don't know what that does or how that works. Honestly, I've never seen it. So we have a planar projection, of course. We have seen this. It takes a slice of the sphere and it projects the rest of it. So northern or southern, polar projections are just the opposite. The antipodal compared to your position gives you the baseline from which you project, the distorted sphere around you, getting more distorted the further away from the center it is. Basic stuff. Conformal would be, equidistant or, grid lines, basic grid lines, which ended up being the Mercator, which you can use to draw ruler-based lines to actually get, directions, because this is preserving, say, where you are and where you want to be, because that is an equal grid. The compromise, like I said, a little bit of both. You got a little bit of this, a little bit of that, minimizes stuff for whatever I want to use it for. You can choose whatever for your current project and invent your own map projection, create it, and then do whatever you want with it. There's 201 of them. There's no need for 183 of them, as far as I can tell. So,
Other than fun.
like, they're literally all people's names, and it's like, so you have a superstar map like this, and you're like, so what did you use this for, though? Like, what was the practical need? You were like, you know what I need?
Yeah.
Like a Burger King crown, but like not all the way. No idea. No idea. Again, I think I'm making the same page, graticule, back to our geographic long lat spherical coordinate system, and running into. I started with this with the Glober, and it seemed to be, readily accepted. So longitude and latitude is inherently spherical. Do people generally agree with that, do you think, or is that like a bombshell?
They're based on the hemispherical vision that we have, so it just kind of follows naturally.
Right? Or even if you don't know how it was derived, if you're like, hey, I have this like infrastructure that has these equidistant circles that get smaller at each pole. Well, it's exactly a sphere. So like all the things associated by a sphere, and you're like, okay. But then I'm going to say that this map, when I project it and distort it, is not giving me a flat equidistant thing. Look at the size of the furthest extremity of the continent. Look at the way it's distorting, and you're like, yeah, that's not because the globe Earth that we're trying to project is not is not being represented curvature-wise. It's because we've inflicted curvature from the sky onto our planar Earth. If you go back to the Sky Mile presentation, the Freemason square and compass thing was a big hint, right? They tell you this all the time, what the square and compass is, hidden symbology. Of course, they're inversionists, so they invert everything. So they tell you, it's one way, and obviously it's the opposite. But there's a whole section on that. Square and the compass is basically planar Earth and the celestial sphere, right? So circle for the compass, square for angles and terrestrials. Again, back to great circles and little circles, but this is essentially all the reasons why longitude and latitude are spherical. So great circles and little circles, spherical trig that's on the backhand coordinate system when you're trying to convert to anything else, the way that you navigate on the equilateral or direction preserving maps. And the last part is the actual angle you're taking based on the celestial sphere is absolutely curved, right? You're looking at a hemisphere, you're mapping the hemisphere, you're saying, why is the thing I mapped from the hemisphere a hemisphere? I can probably help you with that. But it turns out that because the stars are spherical, everyone is able to not even just accept that they think that they live on a sphere, but like argue that that's the case. And so far to go, even if the stars were planar above us, then I would think we live on a flat Earth. And I was like, wow, I didn't actually consider that, but I think that a lot of people have that same kind of perspective. They see the sphere above them and they're like, oh, I must live on that. And you're like, but if you didn't and you saw an exactly that degree on this flat plane, right? And then when you moved, you took that little spherical radius with you, then you would you experience the world identically as if you were on a globe. And honestly, I couldn't get the Glover to admit that. He was just like, nah, but I can do radian transformations and coordinate system adjustments and get back to my sphere. I know it's a sphere. And I'm like, but observationally, it'd be identical. I'm like, yeah, but I can look at this. And I'm like, all right. But if you're looking at the sky and it's a circle, and you're like, how does that differ from my flat plane where I can see in a circle? The point is, it's identical, right? So people who are like, oh, your personal dome, yada yada. It's like, no. We have the same experience, we have the same phenomenon. I'm just backfiddling with the interpretation and application of it, right? I'm not even saying that it's wrong. I'm not even saying the circumference isn't useful. I'm just applying it differently than they are, right? The circumference of a sphere is the same as the circumference of a circle, and obviously there's only one formula, and it's used ubiquitously for both. There's no spherical circumference formula, right? So we're getting that. Anyway, planar coordinate systems are not based on the stars. They are easy to use. They're Cartesian. They are what we convert those things to do math and basically look at things in a cohesive manner. So we went into also on the presentation before spherical, cylindrical, Cartesian, like all the basic coordinate systems that you use. And of course, we went over the Cartesian simultaneity, where your point can be simultaneously described in all of these coordinate systems and the base one that you're on. So it's just some math, and the only way that works is if they're all using the same infrastructure, longitude, latitude, geographic, say, again, the baseline. So when we're doing local maps, this is kind of what we're getting away from the spherical stuff. This is how you actually would practically use any of the cartographical display tools here. Turns out 2-in-1 map projection is only for people on the internet. When you really got to do stuff, you get a local map, you get a grid, and then you correct it, interpolate based on this. Turns out that they all do that, and the Mercator is essentially that the same strategy, localized, divided up all over there. So they just took little small areas, did exactly that, and then combined all the areas together and called it Mercator. So they just took 6 degrees of longitude as an increment. In the same way you can deduce, say, the circumference of the Earth, if you knew that a nautical mile was a 1/60th of 1/60th of 360, then you could say, hey, based on that unit of measurement, the whole circumference of the circle that I'm measuring is, this. You can get the 24,000 nautical miles and something like 25, I think, statute. I forget. But whatever that is, whatever that equates to. So the universal transverse Mercator says separate transverse Mercator projection zones. So using, not the globe. Again, this is why it was allowed in 1500 supposedly, before the longitude system was invented, right? They could do the same thing without the longitude system, shockingly, but they wasn't spherical. They could just divide it by grids, use their ruler, and then when it was distorted, it was over distances, and they would just solve that by making it smaller. Super, super easy, very practical. Again, just basic grid lines. They keep that pretty standard. Here's essentially their interpolation, right? So we're not going to spend a whole bunch of time on this, but the whole point is there are ways to not use inherently spherical coordinate systems and always get spherical results, but nobody uses them except when you're doing things like building or planning or citywide or in anything local, practical, or useful, I guess. Here's how they do it in the US. Local grid lines, again, corresponding loosely to where they put the geographic longitude system. Again, you can kind of get a feel of, didn't matter where they started the circle, whether it was 0 anywhere, people were already inherently using this system and dividing it up. So specifically, when you get down to local, like states have their own coordinate systems, they overlay them, they may or may not match the greater ones, and whenever there's a confliction or a conflict, the local prevails and nobody gives a crap about the geographic nonsense that they say they must adhere to. Let's play with a G projector. So let's do questions, and somebody find me a map that is Mercator or equal area cylindrical, something like the pretty much all the maps that you're familiar with. Someone find me a map that we're going to convert into like however many coordinate systems we find fit, all showing the same data, the same distance, the same continents, et cetera, et cetera. Oh, it's cool. I already have a map in case nobody finds.
I can grab you one. About that boot, Italy.
We need a world map that uses longitude, latitude.
Oh.
Sure. Yeah, I'm not a wizard, dude.
Well, so what? I guess I need to know what you want exactly.
So yeah, not local. Anything that uses longitude, latitude. So like world map, Mercator, cylindrical, any world map that's displaying all the longitude and all the latitude. I guess that's very important. Let's see. I think I have a window open that I saved just in case. Just for the
Can it be like a great circle map?
What's a great circle map?
Just like an AE style?
No. So the G projector software does come from NASA. So it has some inherent flaws, and it only takes 6 inputs to project it into all the other coordinate systems. So it's a little weird, but it's because they want to make you think again that everything is the sphere. Let me see. Yeah, here we go. The thing that I had was a population density map, I think, that I pulled off Wikipedia. Yeah, this one.
It says your stream is paused, by the way.
Oh yeah, he went to desktop. Hold on. Boom.
Google, just making sure you know.
Is it back?
Yep.
Okay. Where'd my Java go? Where world political map. Not exciting, but it is the right style. What is this called? Right. Robinson. Robinson is like the circular one here. I'll,
We see, I think, your slide right now.
Oh yeah, I'm not showing anyone. I'm going on the thing. I'll put it in
Cool.
chat, or no, let's just share a screen. Change windows. Whole screen. This one. And we'll move G projector over here. And we'll get the one map. So I don't have this one actually, the political map of the countries, but we'll use this. We'll put this over here, called the world map. Oh, Windows Explorer crashed live time. Maybe I should be a Linux lad, guys. What happened? Oh no. ready,
Dude,
it's back.
that's one of the that happens to me all the time. Windows crashes exactly, or Windows Explorer crashes like that on me whenever
Yep.
I have to use it to edit videos.
Or like just randomly all the time, I guess. No problem. It's almost like I was prepared for that. And it's called the world map. So we'll go refresh.
It's called a sniffing bug.
It's the you caught the actual virus from someone aggressively sniffing all your packets. It's unavoidable.
That person being Bill Gates.
All right, so here's what we get when we import a map. This is actually a Robinson, so it's one of those hit or miss ones. And as you can see, here's the allowed inputs. Now again, we're using the same coordinate system. We're projecting it equally into 201 various things that are all the same, except we can only start with these 6. Somebody riddle me that. Right, like the way it works is I can go equilaterally to any one from any which one, doesn't matter, but I can only import this, and I can't actually project a globe. So must be because oh wait, no, Bacon actually made it so I can project the globe, and it's exactly the same as all the others. So thanks again for Bacon. Let's import, and we get this. So it starts off with our globe. Hey, but we can from here do all sorts of things to this data to make it appear any other way while actually changing nothing. So let's do, say, azimuthal, our favorite, equidistant. That's actually what it would look like if you adjust for the correct longitude and latitude. Again, the basis. How's this big? There we go. So take that Robinson, we had an equal area, we took a conformal, we imported it, and now it's, look, it's all skewed and wrong in this projection, guys. What do we do? Everything's different. Or it's exactly the same, right? It's all the same. It doesn't matter, or I couldn't do this. Right? Or this. Literally every which way is the same. Nothing is changing. All we're doing is looking at it differently. We're slicing up our theoretical sphere in all sorts of interesting conformal, cylindrical conformal ways, and we're getting these results. None of these. Look, if you need a Wagner map, there's actually 9, and they're all through Roman numerals. So the difference between Wagner 2 and Wagner 9 is who the hell knows? This is like, who the hell is Wagner? Dude, you also get the Winkel-Trufel.
Those are literally all different types of projections.
Huh?
Those are literally all different types of projections.
These are the types of projections. So when you're like, there's 201 available projections, like these are them. And again,
Right.
if you want to make one, you just have your name and then you put a name on it and then you just do whatever you want, I guess. And that's how, like, honestly, besides Mercator, conformal, equidistant, AE, and orthographic, they're all retarded. They all have like one use that could easily be done by any of the projections I just listed. So not sure why we have so many, except that,
Just
they
because
do
we can.
love to
Right.
befuddle, dazzle, and confuse. So if they say present this to you and you're like, hey, you know what you can't do? Just put that in a globe. You guys know why that is? You guys know why? Because the globe, we live on a sphere, and that's proof. And they'll always come back to that. But all you're doing is starting with the globe, measuring the globe, and concluding globe again. So let's take a look at, say, equal area. All right, so some of them have actual descriptions, like equirectangular, your reference is familiar. What we can also do is say, decide to add longitude, latitude. You remember that dude on Flat Earth Friday who was like, or actually, let's start this. Do people think the Gleason's map is obfuscating a longitude section or a meridian or some part of the area? Do people believe that? Is that something that people say?
I have no
Probably.
idea.
Because I
There's a
heard it.
scale factor on it.
Well, yeah, the scale, but they're like, hey, you're just missing 7 lines of latitude. I counted. I heard someone say that, and people were like, yeah, I don't know. And I'm like, what? No, that's not how it works. It doesn't.
that was some troll. Yeah.
Okay, but all right, well, that's good then. It's probably restoring my faith in humanity. Let's say we're at them at 60, right? So we'll do these grid lines are appearing. We're equally assuming them based on, an arbitrary increment along these longitude latitude. Basically, you can do anything you want. And if I put them on this projection, I can also have them say labeled, right? So we're looking at longitude measurements. Here's the separation. When we go to the other projections, they stay there, right? So Projector, super free, based in Java, great program, super cool. Doesn't do orthographic globe project. Oh wait, no, doesn't do an input as a globe, but will allow you to do, I think, orthographic. Let's see. Yeah. And then bring it up. There we go. Yeah, I forgot how loud I type with next to the keyboard. So yep. So anyway, every projection, every available way to look at it is always the same. You've changed nothing. You've just looked at things through a different conical or azimuthal slice. That would be the whole. All right. Unless anyone has any map projection questions for G's projector, or if you have a map that you think proves sphericity or that can't be converted, let me know.
Well, so the confusion, right, seems to be that people think that because it's not, people expect it to be like a, they don't get graticules, I guess, essentially, is really what it comes down to. People expect to have a congruent map that is going to have equal distances along longitude and latitude, even after transformation, which is just, kind of asinine.
But the thing is, like, you have longitude and latitude in each one of these projections. Whether you paint it on, you measure it, you divide it up differently, it's because of the longitude and latitude that they're able to do equal area, equal distance, as in equal direction preserving. That's all from the baseline, right? They can't preserve qualities of a thing they're not a part of, if that makes sense. So the qualities that they're kind of sacrificing are all, based on, or actually are all well contained in the sphere. But again, the only thing that you're projecting is that base coordinate system in every which way. And we'll get to like mainstream Wikipedia and ChatGPT later, because it's pretty funny when you ask it this stuff. It's like, well, map projections work this way, except for the AE map, which is totally different on its own by itself and not because of flat earthers. Like, wait a second, can you go back like two sentences? Why is that part of the azimuthal equidistant area projections different than the other azimuthal equidistant area? And it's like, oh, I'm sorry, you're right, they're all able to do that. And you're like, okay, I'm gonna need
It really
you to
said
ask.
that?
Absolutely, I'm gonna need you to dig deep and explain why you keep lying to me directly before you give me the truth on this specific issue and these other 4 issues related to flat Earth flight paths, flight path map comparisons, etc. It's like,
That's hilarious.
it's really funny. And there's a whole bunch of those hurdles set up that it's like, hey, this is one way, except like the nautical mile is definitely based on a sphere. It always has been. Historically, this is what it was defined as. And you're like, historically, you said it, so I know it's true. Gotcha. Damn it. All right, back to our Canva presentation. My dog is just whining, dude. I think he has to go. How am I going to do this? No,
Yo, if
I'm
we
just
gotta
gonna
take
leave
an
it in.
intermission, we gotta take an intermission. Dogs,
Intermission.
dogs gotta go. Dogs gotta go.
I mean, of course, I took him out
Please.
right before this, and he was like, "Look at the other dogs, and here we go, la-di-da." And I was like, "Dude, I swear to God."
Intermission, just play Olive Stone songs. There you
Oh,
go.
is he here?
Yeah.
He is here.
He is here. Excellent. Well, this is a nice time to do a quick. How about a new reel of the latest 2 videos? Maybe someone want to stream that to the stream,
You the boss.
and I'll do like a 6-minute quick walk with a run.
Alan or Beast, I can kick up Miller's assistant.
You want me to share?
If someone can, otherwise I can boot up Windows Virtual Machine.
Doesn't Alan have 7 bots ready in case I was going to make fun of him for not being able to do this immediately, or did I make that up?
Yo, sorry, I had some gratulators. What's up?
You had some what?
We're gonna do a quick little intermission so Shane can step away, take the dog
So
out.
Shane can go poop.
Yeah, Levi has been whining the whole time, and I don't know how long I can chance it and press him. So give me like 6 minutes. I'll be right back.
Cool. So we were gonna maybe stream some stone music in the meantime.
Nice. 1 second.
Cool.
You're doing it?
Yeah, I got you.
Cool.
I'm gonna roll.
Thank you,
I'm gonna
sir.
roll a fatty.
Not a nice thing to say. Oh,
Yeah, I'm
we
going
go.
to throw up my live Discord, and whoever's streaming, there you go. Perfect. All right, I'll be right back.
nice. All right, so yeah, everybody, we're just gonna do a quick little intermission here and kick back and enjoy some Stone parody tunes.
Hey, NASA liars, you just think your globe's so pretty. I'm 100 miles away to clearly see that city. How about you? Does math explain this? I want proof, not some old goof. FE deniers, don't you worry about the distance. I can see you there across the lake while laser pointers glisten. Use your eyes. Just hear my words, see through the lies. Might be surprised. Globe, no way could it be. No controlling how we think. Stop your lying through your teeth. No, it looks quite flat to me. Appears quite flat to me. Hey, NASA liars, your deception spread so far. We all believed your lies 'cause we were young, but now we've seen the water. You're no good. Just believe because we should. Wicked brotherhood. Hey, NASA liars, I've got so much left to say, but does it matter that I say to you gas pressure is contained if there at all? With gravity it does not fall, it fills it all. Lord, no way could it be. No controlling how we think. Stop your lying through your teeth. No, it looks quite flat to me. 100 miles, it's all the same, and we've got pictures from jet planes, and where is all the curvature they claim? Our friends are making fun of us, and we'll just laugh along because we know the truth no matter what they say. The liars, they made fools of us, the tinfoil has been left to rust, and now the world will never be the same. Let's end the game. Hey, you know they're no good, and I know they won't trick me like they did for years and years before, and I'll be asking them to prove their claim. Now things will never be the same. It's time to beat them at their game. Yeah, NASA lies to me and you. You know it's true. Lord, no way could it be. No controlling how we think. Stop your lying through your teeth. No, it looks quite flat to me. Appears quite flat to me. Fake globe. Fake globe.
Very nice.
Lats and longs, lats and longs.
Little lats and longs, you say?
Yeah.
Gotcha, Brody.
So
One-
awesome.
Yeah,
one
that's
second.
appropriate.
Clamor for it.
Considering the stream, makes sense, right?
Definitely.
Indeed. All right, here we go. You said gratitules and what now? All right.
Longitoids.
Longitoids, that's it. Thank you.
Gratitude.
A little dig about a master plan. Gonna make a geoid out of this flat land. Sky's looking like a big bowl of stars. All we gotta do is plot the lands like they are. Sucks that it's a plane, and this won't be a breeze. Have to make a curvy map made to match what we see. Someone says since we're lying, we'll just use gravity. We'll deflect the vertical and adjust as we please. Saying, oh yeah, we'll have lights and longs lined up to the sky so you can't prove it wrong. Saying, oh yeah, we'll plot those lights and longs long after the shales and globe is all gone. Little taken back, making them long lines meet, scratching our heads, but we figured out a perfect scheme. Well, whenever there's a place that has to curve like we need, and the royals paid to make this geoid a thing, so we'll say, oh yeah, we'll have lights and longs lined up to the sky, so you can't prove it wrong. Saying, oh yeah, we'll plot those lights and longs long after the shales and globe is all gone. Oh, what a rock! Keep control. Belts, they deny us soul. Holding on to the ski as long as we can. No change coming round real soon for dumb women and men. Oh yeah, we'll have lights and longs lined up to the sky so you can't prove it wrong. Saying, oh yeah, we'll plot these lights and longs long after the shales and globe is all gone. Plot on. Little did it about a master plan, making sure we keep our rule, make a fool out of man.
Very nice.
Woo! Woo!
So, did we have a Shane back yet, or no?
That's
Wiping.
8.
All right,
Well.
Stone, make another song quickly.
Can you whip one up?
Get
real
your,
quick?
get,
Yeah,
get your saxophone.
Yeah, we should. Except my wife's asleep on the couch.
We'll wake her up then. Just
Dude,
fine.
she doesn't like waking up to the sound of saxophone in the background.
Nah, that's obviously
Actually,
a
she
lie.
kind of does. But let me tell you.
Everyone likes that.
Yeah, she's trying to constantly trying to get me back into playing. That's for sure.
Really?
Oh yeah, she's pretty vehement about it.
Nice. The music is a good thing, man.
Nothing like it.
Indeed.
Well, do you want to, Stone? Do you want to give your kind of maybe synopsis of what Shane's gone through so far? I missed the first part of it myself anyway, but I don't know if anyone wants to kind of try to summarize what they've learned so far from what Shane's doing, or talk
Well,
about any of
Toby's
it.
good
before
on
we
the
get going?
recap. Let's let him handle it. You're totally there, man.
All right.
A lot of discussion about spherical trig and about projections and just about how that all works. That's essentially been what we've been going through, is just really going into detail about the way that those projections work and about how no matter how many times you project something, if you're using, or, transform something, if you're using a longitude and latitude system that is based on our spherical vision of the sky and then transformed to make it appear to be a globe beneath your feet. If your starting map, wherein you're actually mapping the land, is based on that, then it doesn't matter how many times you transform it. As soon as you introduce longitude and latitude, two things are going to become true. One, you're going to have a, at least probably quite accurate description of what you're going to see in the sky from that longitude and latitude position. And then two, it's going to work just like the map you have. If it has longitude and latitude, it's going to work just like a globe projection, but it's going to be relative to the scaling of that map. So that's kind of what we've been going over. We talked a bit about the graticule, and Shane kind of discussed how that's what, we need to all become
Yay,
familiar
Shane's
with
back.
that term. Yeah, I see that you're back, Shane. We had a quick request for a recap. I was doing my best.
Excellent. Did you on the spot summarize it perfectly?
He was nailing it.
Pretty much.
Nice. Didn't even hear it. Pretty sure that's what happened.
Well, I'll finish up the last thought I was saying there, which is just that the graticule is essentially the projection of the distance of the lat and long, and understanding that concept is really key to all this.
Yep, everyone should be Googling graticule right now and finding the same. I think. I noticed when I used it on Omnivore, it only took 4 times before he was like, "What is that word you're saying? How do you spell that?" Okay, all right, I'm gonna go see what the hell you're talking about, because
Yeah, and up until then, he's like, "I know you're wrong. I know you're wrong. I know you're wrong." And even though you just told me what the word is, I should look up. I still know you're wrong.
but he wasn't a total dick about it. Oh, you were there for that? Nice. That should have been recorded because it was a nice
No, I
walkthrough.
wasn't there. I just assumed that's what he was probably like.
Oh, yeah, nailed it right away. Could have fooled me, dude.
Yeah.
He's like, well,
That's
no,
funny. You were there for that?
I was like, wait. Oh yeah, no, that's a pretty good assumption.
No, he's just on repeat. That's all. Yeah, he's one.
I was like, so it wouldn't be different to your globe and my planar sphere with the same viewing radius. He's like, yeah, but I could compute sphericity if I just invert the coordinates and do back. It's like, okay. I get it. I was like, look, they're equivalent. He's like, no, but globe. I'm like, okay, valid point. Let's move on.
Yeah, I love when you go through your presentation and how you're so good at reiterating the thought process that the globies or any of us used to tend to do when we're just reifying the model, and how it's so easy to just do the transforms and just think that must be the way, the assumption along with it. That really helps with anyone watching. I'm sure that can get why people are so sure of this still, even though there's all the evidence in the world. That's not the way it is. Yeah.
Yep, there are people who live in this coordinate system and need no further verification. And even though everything always comes back to this, they've never questioned why it was there in the first place. That's kind of what it is. It's like you can measure a distance on Google Earth and WGS84 and satellites. You know, I'm like, whoa, that's all the same thing. And guess how they determined that? From looking at the stars and then literally marking out on the Earth where the stars are. we'll get to that, but turns out if you can name one zodiac constellation, you can plot where all the world is landmass speaking based on what time of year it is. So that's interesting, and that'll be the end, I think. And we lead into cosmography, and we see how the stars are everything. Which, again, if you start flat Earth and you're like, okay, here's the deal. Look into the truth, but don't ever look up at the sky and don't worry about it. And I know it's not important. Just, try to prove the shape without doing that. And then it's like, oh, but all the other arguments are about that, though. So yeah, don't worry about that. Just keep talking about whatever. You'll definitely be fine. And I'm like, well, if they took that sky and inflicted it upon the ground and actually made that sky the grid work from which everything is done, computed, and derived, shouldn't I look into that? Yeah, it turns out you need to know that because that's how everything is made. That's what they did. And if you go about your day as if everything is not inverted, you will be led astray, essentially. So the AE map, the famous Gleason's, the flat Earth map with wrong continents and the shining de facto example of how retarded flat Earth is and how Toby, Shane, and Alan misunderstand all maps and how we should have 7 one-person spaces to talk about it and see if that solves our retardation or whatever. So it is of the class azimuthal equidistant, right? So it is projecting the same graticule in a central, they call the northern polar projection. So they take a point on that sphere, they put a plane on it, they project the rest of that sphere around that point with more distortion occurring the further away from the central point you go. Now, let's see here. Okay, all right. So let's go right through the Gleason, the azimuthal. So this is the main argument I want to use the Gleasons for. It's the difference between geodesic, a great circle, and a straight line, or difference between, say, a chord and an arc length, or the corresponding, straightened out linear line of the same distance in a curve format. Essentially, like the radius of Earth, 3959, is from a sphere. Straighten that sphere out, it turns into 6210 statute miles, just based on 69 miles per degree and 90 degrees of separation gives you that total amount. So why is that not the radius of Earth? Because geodesic arcs and line. That's why, right? Is everyone good with that? I know I've talked about that excessively, but maybe people have missed it.
Seems good.
All good. Keep going.
Rocking. So my favorite, the Haversine formula that people are like, this guy thinks you can use Haversine to get distances. And it's like, yeah, if the whole world is in the coordinate system that the celestial sphere is the globe Earth, then hell yeah, I can compute distances within that system to get the same distances from which I started. Of course I can. You just have to do all the angles, trigonometry, cosine, and functions that would get your, say, co-altitude or reciprocal amounts, or like if you add 40 latitude, you're gonna get resulting corresponding 40 longitude, right? It's a system. You get half of it. They're called tuples. So you get a coordinate is a long and a lat, or east and a west. 2 points describe exactly where you are with no height. That's how it works. That's what we're talking about. Every distance, every point is not a line. It is not the chord. It is the arc length. We are computing geodesic arcs of distance on the globe, on the sphere, on the celestial sphere, on the graticule. All distances are these geodesic links, right? If you ask ChatGPT, just, for a basic, quick understanding of the digestible mainstream version, they'll quickly tell you, yeah, that's all based on that. This is how we this is how we derived it. Here's what we do. Here's why it works. Interestingly, if you're like, my azimuthal equidistant, it'll immediately be like, yeah, but it only the skews continent sizes and it isn't accurate for distances. And I'm like, well, hold on now. All the other maps of that type are accurate in distances, and this one is no different. Using the same coordinates, why would it be? And it's like, oh, you're right. I'm sorry. It absolutely can if you're going to use the geographic coordinate system that you started with, but only because it was like, well, why do I have caveats for this one map than not all the other maps that all can use the same thing? You see what I'm saying? Every map uses geographic long lat. So if you have one long lat, you can get the distance to any other long lat. no matter where you are, what coordinate system you are, because it's always going to be spherical. Everyone cool? I know I had a talk with Jesse.
No, yeah, we're all good. Yep.
Jesse killed me with this one for 2 hours. He was like, so about the Haversign, can you get real distances? Yeah, you were there, dude. It was so hard. You were so honest. And I was like, we concluded 2 hours later exactly where we started, and you were smarmy and knew about it the whole time. I can't talk to you anymore. This is ridiculous. So all distances are geodesic arcs and curved. So do we know real distances? Let's call it, we know X. We know X is consistent and verified every which way we test it. Again, globe to globe to globe, or celestial sphere to angles to the stars to geographic longitude lat to inherently spherical graticule. Now, here's just a page from one of the many papers you guys should definitely peruse through if you want to take a gander at how this actually works. This one paper is all just talking about the sphere to the plane and mathematically how that works and permutates and etc. Not going into the deeper application of why we're starting with the sphere or what the sphere is or where it comes from, etc. But this is just one example of how it starts with the graticule, saying, hey, equally spaced straight lines and equally spaced parallels, showing essentially concentric circles, one great meridian, and spheres, sphericity, spherical all the way through. Now, about the Gleason's map, which again is of this type in this coordinate system, can compute every accurate distance, shows the same size Australia as every other map, just in its conformal way. If you take a point geographically along that point to another point and compute it on the azimuthal equidistant, you will get the correct distance. You will get that because aspect of the azimuthal is it straightens great meridians. It treats this great arc circle as a linear line. It has to, because longitude, the way that it's grid line and based, is based on that curve. And the sphere, it's a curve. When you straighten it out, it's a line. Then you can't use that line to compute and compare all other distances without it being a line as well. That's just the way that that works. So on the back of the Gleasons, from the patent, with words of Gleason himself, he puts in no other words, listen, fuckwit, if you don't know how to, no, I'm just kidding. What he says is, I actually included 2 different arms that will let you compute the longitude portion of your tuple, which will get you your distance and position. Everyone knows latitude. Latitude is easy. It's marked. But to see what time it is on the longitude, to see where that celestial sphere will be passing overhead, to accurately compute where the geographic equivalent spot would be on Earth, you have to do this, right? You have to get both halves of your coordinate system. So people assume, I guess, that if it's displaying a visual distance scale, that's incorrect. But again, if you measure the grid lines and compute distances, that's exactly the same, no different at all. So this one is essentially just saying, look, there's an arm, you can take your time, you can determine with this arm your longitude, component, and here's how you would do that based on this conversion, 0 round numbers. He actually talks down to everyone, I think, in this back. It's really written kind of like, if you don't know this, then you're like an ignorant child, essentially, which I thought was humorous. He kind of treats most of the people like that, actually, if you read his book, especially his friend Dimbleby, who actually was brilliant, a chronologist, and mapped out all of the eclipse cycles. So them dudes were G's. So it says, Greenwich meridian. So after they already determined longitude and latitude, Gleason was like, I want to make a map. They were like, cool, listen, here's the deal. You can make exactly this map or nothing. He was like, can I project? No. All right, what if okay. All right. So he gets a patent, does what he can, makes it flat, and then uses it to preserve, an accurate direction conformity so that you can compute actual things like, flight maps and directions. And, azimuthal is one of the more useful projection types. So he decided to go with that, essentially. And here we go in his own words saying that here's how you would use my map to get your globular celestial sphere curved, geographic, long lat, graticule distances. I'm just going to say it like that every time so we can really nail it home. How many different ways can I say curved? So again, the Gleason's map, it's also a sun map based on celestial observation. So longitude and latitude based on celestial observations. So we're looking at a inherent curvature of the sky being measured, mapped, and then translated to a plane. So if we do see spherically and live on a plane, this is exactly what it would look like and how it would work, right? So just gonna nail that home too. We have a couple really good animations that I threw together that should also convey that. So the sun map, meaning that you can take your latitude, get your parallel, compute distances based on that. But if you have your long lat, you can just get another long lat and do the wonderful things in Excel on the internet, Haversine conversion, etc. Radian trigonometry that uses radians and offsets to get back to the coordinate system distance that you started with, always and always. And this is, of course, the ruler on the back of the Gleason map. Oh, maybe this is why people started using a ruler. I think I just got it. Like, that's not what that means, guys. It doesn't mean take this and measure distances according to the scale. Cut this out and measure it. No. It shows you based on the a number line and a scale and a coordinate system what this. Oh man, wow! I just got that. All right. So yeah, that's not what the ruler is for. That just shows you that it is measuring geographic longitude distances, right? It says 60 miles to the degree, essentially confirming, hey, within this coordinate system, this is how we derive everything. Cool. So does the azimuthal display the same distances? Yes, unequivocally, absolutely, without a shadow of a doubt, yes. Does it preserve straight circle distances, true distances from the point, and celestial objects? So it preserves two of those, right? The azimuthal part of the inherent flaw is that it takes things that are of a certain distance above you, say infinitely or light years or whatever, then it puts them at, say, broken altitudes or in a sphere in an equidistant radii around you, all around you. Like in the nautical mile presentation, we went real deep into azimuthal and cylindrical back and forth coordinates and how that works, and how I'm pretty sure that's what the coordinate system would be for the celestial sphere and the Earth, as far as what we see in the sky and how we interpret that and interpolate it to our planar Earth, right? Or to our mistakenly to our planar Earth to give it sphericity. Speaking of sphericity, all of this is based on the graticule. So what is curved? Where does the curvature come from? Something is curved. Everything is curved. If it's not the Earth, what the F? So again, you can just bullet point, Google research, ask ChatGPT, get a mainstream consensus, do any number of things. You'll conclude that coordinate systems that are based on the stars, angles to the stars, are inherently spherical. There's no way around it. There's no other way it could be. If you see things in a sphere and then you map things based on that sphere, how could you get anything but a sphere? Or in this case, a hemisphere that you mathematically complete with its corresponding antipodal version. Exactly that. Mathematically sound, right? The circle that goes across the Earth could be the same circles as that goes underneath your feet in the supposed celestial sphere, back to the circumference of a circle and a sphere being the same. Everyone see how that gets confounded all the time? And they're like, yeah, but based on this, it's a sphere. And you're like, all you've done is repeatedly measure a circle and then incorrectly interpret that to everyone else. That's all that keeps happening. Thank God that we already have some sound math that actually computes that spherical radius based on how far you can see, and then tying it to optical limits and resolution and things. But some cool guy probably put that together. We'll just assume that that's all right. Oh wait, we have to go back and read that. So yeah, these are the coordinate systems that are based on stars. Some of them. We have the horizontal, also known as alt-az, or as we started this journey on the Star Trails version, the azimuthal grid of vision, or the azimuthal grid, was always what we started with, right? That grid in Stellarium, it's alt-az, that's the coordinate system. It's your personal way to mark it, but you can't tell me based on your alt-az where that star is and have me find it. That's why they need the celestial equator and the comparison point. So we have the one angle based on angles to the stars, inherently curvature. You're taking the things you see in the sky, you're mapping that to a theoretical corresponding, which would mimic its shape and not be anything else. Equatorial coordinate system is, again, very similar, except based on a sphere that you divide in the middle of that great meridian in the way that you start every coordinate system as a sphere. Geographic, we've been dealing with a lot, long lat. Typically geocentric, we'll get to that later, but it is just a combination of actual coordinate systems that are based in, math, number lines, and nothing retarded, called Cartesian, spherical, cylindrical. We just use actual math with number lines to, display, work with, add, change, manipulate, and test things, points, maps, observations. There's nothing wrong with that. Not based on any curvature, is no star. It's just math and a grid line, essentially. So that's why Cartesian XYZ can be simultaneously existing as a polar coordinate projection, as a cylindrical, as a azimuthal, and in literally every Cartesian coordinate system, because you can convert all of them equally back and forth. We went over that pretty extensively, but I'm just going to move right past that. Although this is kind of the crux of it right here, right? It's coordinate systems based on angles to the stars. If you think about it, this is what we're looking at. This is what we're dealing with. This is what we're measuring. And this is why we keep getting sphere. Keeps coming back sphere. I don't know why that is. What do you guys think?
One sphere to rule them all?
It's spheres all around. I don't see anything except, oh, wait. Turns out every sphere is just a plane with a circle around it. It looks like, it's like, oh, look, this sphere. And then, oh, look at the circumference, guys. It's always the same. Circumference, 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 circumference. It's just the middle of the sphere. Wow, that's super interesting. That's what Eratosthenes supposedly measured, everyone knows, based on the sun to determine a, quote, circumference, and was like, behold, sphericity. And nobody was like, but what's the formula that you're using for circumference of the globe that differentiates it from that circle again? And they were like, shut up, don't worry about it. We don't exist anyway. This is just for Wikipedia.
Yeah, but then Cryptosthenes actually proved him wrong anyways, so.
True. And he actually was real, as he says so in his spiel. So then proving, the flat earth way back then, 2,000 years ago, and then proving that the measurements he took actually not only confirmed distances can vary, but that it's always the same circumference. Yay, circumferences.
And Biasticles witnessed all of it. There you go.
That's true. We have two Greeks that dude, that's better than the inventor of longitude, sextants, all celestial navigation, the grid system, and all sphericity, Hipparchus.
Oh, you're going to question Hipparchus? Come on.
No, I don't question it. I know he definitely did all those things, wrote all those books, has no evidence, and only exists in a paragraph on the internet. I definitely believe him. Anyway, these are just background coordinate system gifts from other presentations that I thought would be helpful. This whole thing is going to be distilled down to like a 15-minute reel on our next presentation as well. So this will be digestible, conveyable, translatable, and take homeable, I guess, by the end of the week. So no need to take notes. I'm sure everyone's doing that. So here's a visual demonstration of how we can get confused with what we see in the sky and what we live on. Right, so it's not the globe, it's a meridian that we divided in half, and you're like, wait, I can take angles to the stars, and here's how big my Earth is. And you're like, I can take not only similar but identical angles from my flat plane if I can only see that far. Wait a second, you're on the globe. Nope, just looking up. Wait a second, is that the flat Earth in the middle of the circumference of the sphere? Nope. Oh, it turns out it was that the whole time, right? Like, whoa, no way. They're literally mathematically identical, observationally identical. You wouldn't be able to tell whether you're on this plane seeing in this radius or on this ball. It's not any way to tell the difference, as well as every glober will say, nah, I would definitely know, and it's different. And it's like, well, no, you wouldn't. And you have to believe that or you would be retarded.
Not to mention all the direct experience that tells us we're on a stationary plane.
Yeah, so in order to countermand every observation, measurement, and thing I see, and to live in a world of consecutive illusions, I need a little bit more grounding, but that's just me. It's like I'm not ready to be mind controlled by having someone convince me everything I know is wrong, so I have to trust inherent authority, and you can give me things that you want me to know. I'm going to do my own thing, see what happens. Well, this is a... that was pretty quick. This is a quick amalgamation of my favorite coordinate system, the spherical, right? This is spherical, polar. It's just showing you how those 3 points get translated when you're doing, say, Cartesian, cylindrical, equirectangular, or a whatever one I missed. Spherical, I think. No. But anyway, these are all instantly relatable. Global, not global. Let's put it planar Cartesian simultaneity is real, unlike relativity simultaneity, which is retarded. Everyone's cool. The other coordinate systems based on the stars, as we said, alt-as, our favorite grid, based on observer. It's personal, not relatable, and can't convey to someone on the other side what you're seeing and how they can find it. That's basically the summary. I'm going to try and go a little bit faster here. Who's here? Dude, this is something
Take your time. You're doing great.
I was looking for Napalm because Napalm showed this to me the very first time I saw it. It was the first representation of a celestial sphere. You guys, You see what I'm looking at here?
Yeah.
It was a
And yeah,
brown
for real,
one, I
take
think.
your time. You need to go long. We're all good.
Yeah, I did a practice run and it came in right at like, besides the dog walk, I think it was like 100 minutes. So if I go like just a little bit, it'd be perfect. But if I'm going too fast, we'll just chill. This celestial sphere right here is what gave me the whole understanding. You see how it's a plane with a bigger sphere, and then they think the sphere that you're on is actually there. What they're doing is creating a tangent plane, how you get level on a sphere, you have infinite tangent lines all around. They're creating a tangent on that plane and they're projecting from that tangent, namely being you're the tangent, you're the azimuthal center of this projection. They take that tangent and they project all of the stars about you in exactly the same radius they tell you the globe is. And this picture, I think, kind of nails that and sells it, I think, really, really well. And then it's, of course, someone found it and then used it to depict what a horizon coordinate system would be based on. Again, it has to divide what you see in the middle to be able to get longitude and latitude. That's the main starting point. Without that, you can't measure anything. And so they take the horizon, which is their divider, and they take measurements to the sky. What they don't see, they assume is there, and then mathematically create, right? If you have a hemisphere, turns out the math you can make spherically work and take proportionate, chunks of that, and it will always yield the same result. So no big deal, hemisphere or sphere. If you only see a hemisphere, you can rest assured I can describe that sphere mathematically, no matter what. And then the bigger one would be right ascension declination, the literal celestial grid. Oh boy, look at that picture right in the middle of that text. That's all right. I know what it says. So it's the equivalent of long lat. When you're, say, trying to map a geoid or a ellipsoid, or if you like trying to put a celestial sphere into a globe Earth, you would need to coordinate, interrelate, and equivalate right ascension declination and longitude latitude. Right? It's just the same sort of concept on each corresponding sphere, but they are slightly different, right? Both, one of them is Cartesian and one of them is dependent on time. The sidereal time computing, 15 degrees per hour, or the radial velocity of the sun, or that component is the missing component to create what we see in the sky on the Earth. We have the different breakdowns there. So we have the sphere being divided by that meridian almost every time. No, every time creates a hemisphere. If you look on the right, that hemisphere is identical to the globe on the left. After we created a great circle, divided it in the middle, gave us a prime meridian. Now it's visually, mathematically, logistically, and practically indistinguishable from the corresponding planar version on the right. Right? Circumference. Everyone cool? Ooh, geocentric. So we love this one. Just going to quickly go through it. It's the combination of from your center and that planar sphere that you drive through it. Again, your dividing line, your horizon, your great arc, your central dividing point from which you make all other measurements, parallel and perpendicular. That's what you need for coordinates. So it does that here with Cartesian, spherical, and then to actual mapping number lines, which is a basic Cartesian to spherical, and then goes to the other, I think that there's a cylindrical component, but geocentric is just using Cartesian variants to describe things as they relate to you. That's the whole point. Geocentric, you, the center, away from you. Also, you have azimuthal, we are the center. Cylindrical, we are the center. There's a lot of projections that deal with you being the center of everything. It just seems to work out that way mathematically, but I'm sure it's because we're actually expanding in every direction, all the way from everything spinning out of control in every direction. So again, we started with long lat. We said it was a graticule. I said it was curved. How do we know it's curved? How do we know that? How would we deduce that it's curved? Does anyone want to take a stab? Tough one.
Look at the sky.
Pretty good observation. I like that. I was like, I see a sphere, I map a sphere. How did I end up with a sphere?
Is it that it uses the lat long system?
Right, but how do we know the lat long is inherently spherical? Because we're already agreeing that's the basis of everything. The Globers seem to be okay with that. And then I'm like, it's inherently spherical. And they're like, yes, no, maybe. Depending on what you say next, I'll tell you what I think about it.
Because you can only see so far, and you can only see so far 360 degrees around you.
Which is actually the
Which creates an
literal
illusion that it's bigger.
definition of a spherical coordinate system, as it puts those points in the sky at an equidistant radii around the observer in every direction. that's interesting in a little bit more detail.
So you look
than
at the
me.
sky. Got it.
Right, but there's like 4 or 5 different ways that we could tell, right? So the sky is the main one, the one that I was going to go with, but I couldn't quite articulate to anyone why that is. Like, oh, look, it turns out there is no sphericity, it's only on the sky. And they're like, no, I think that's wrong. And you're like, okay, I don't, touche, fair. I didn't have a follow-up. I don't know what else to say. It's like,
Perspective? Are you getting that? Is that what you're trying to get at? Perspective.
Yes, in your perspective of the sky.
exactly. It's
Perception.
based on your perspective. So if you see in the sphere, you live on a sphere, or if you have a limit of vision, all those things would be interchangeable, indistinguishable from each other, and be observably exactly the same, right? But the other things are indirect. So you can do things with your basis, and you can do things like great circles. Turns out an actual great circle is not only an aspect of sphericity, but like a requirement for every coordinate system. And you can't have it without mapping it, focusing on it, and just sailing it. And all of Wikipedia history is full of people who were just diligently sailing these great circles through the 15, 16, 1700s before they had longitude somehow, and were just trying to map out the meridian of the great sphere that everyone knew they were on. Turns out they had actually run lines that were just lines that acted more like the corresponding circumference of your planar spherical, your planar Earth with your spherical vision. That would be exactly the same, but they didn't take it that way. They decided to go with the great circle means sphericity. So the other part that's pretty telling is spherical trigonometry is inherent. Now, some people will argue you don't use spherical trig in celestial navigation, and I would agree. Directly, you don't, right? You take an angle to a star, you compute it based on basic trig, and you do like sine, cosine, you say distance, hypotenuse, here's where that is on the ground position. The missing leg is the distance. All done. But if you say you want to make use of that observation, you have to convert it back to a coordinate system that you live on. So when you convert celestial to geographic, or when you convert things in the sky to the Earth, or when you convert from the celestial sphere to the pseudoscientific globe Earth, you are doing spherical trig. You are taking radians, cosines, you're doing an offset, co-altitude. You're assuming that the bottom half of your sphere is mathematically there, and you're using math that derives that or depends on that directly. So that's the other part I think that helps people to think it's a sphere. Mathematically, it's a sphere. Right? Mathematically, it's a sphere. But what does that mean? Yeah, it means that you have a vision radius that's not infinite, and it is definitely mathematically derived, constant, consistent for everyone, and it just so happens exactly the dimensions of the Earth that they said to be live on. So again, based on coordinate systems to the stars, we're just going to look at the sky. We see it's curved. We're like, if I had to describe it, I'd say it was like an upside down bowl over your observer, and that's what you see, a hemisphere. Super easy. This is just some basic information going over aspects of a sphere. If you're going to go with the celestial sphere, then you have to use antipodal and opposite, the bottom of the sphere, offsets, and what they call a time-hour calculator, right? When you're converting longitude to right ascension, or that you're converting a longitude to your time component of the celestial of the ether wind, essentially, right? Moving all them stars around. Boy, we got to get rid of that. So if you can use math to predict when you will see objects that set, say the sun, if you use math to describe when the sun will return, and you're like, hey, when I don't see it, right, it continues away from me on this sphere of a circumference beneath my feet, and then comes right back on the other side. And you're like, counterpoint. But what if it goes in a circle exactly that you described, but instead of beneath your feet, out beyond where you can't see? Mathematically, those are indistinguishable, but they never mention one and only talk about the other. So here's our planar Earth with our bowl on top of us with a grid system and stars. So if it looks like this, we can think about it like that. Here's a great representation of some Canva tools and how this happy stick figure in the middle is exactly living in a globe Earth or a plane Earth. From here, he can't tell. He has no idea. Could be either one, right? That's the whole point. So even though we only see a half sphere, a hemisphere, we do act as if it is a full sphere. We do math, coordinate system adjustments, and observations based on that assumption. So the celestial sphere is not wrong. It's not illogical. It is practical and useful and very consistent. When people keep asking, can you compute distances? It's like, I can always get geographic longitude or latitude curved geodesic arcs. I can always get distances based on that sphere. Is it right? No, but it's always conformable. It's consistent as heck, right? If you keep using that coordinate system and you do some math in that coordinate system, guess what your results will be? Different coordinate system. Yeah, just kidding. Oh, wait, here's a good time. That bottom right there is the geographic, now the ecliptic plane, the celestial equator, and the galactic equator. So that's 3 coordinate systems together. Notice that each one is based on, dependent on, and started with an equator, an ecliptic, and literally a mid-dividing line. That's the only way you can start to do it. It has to be that way. But those are 3 different variants of angles to the stars, all doing the same mistakes and inherently dealing with the same induced sphericity. So another way to prove that the geographic starting point is spherical is that we see a dome-like shape above us, and that we compute distances and observations based on that fact, right? There's a thing called spherical excess that people like to think exists on globe Earth, because you can have 3 points that are equidistant, but actually it can only happen on a sphere. And it turns out that's based on the sky in something called an astronomical triangle, which is the basis for a spherical excess, can only be done on the celestial sphere, and was typically used to compute distances and do celestial navigation, knowing that it was based on a sphere. So they would just take that sphere measurement and then convert it to the planar Earth, as Mitchell from Australia mistakenly still believed, right? It was like nautical miles is fine. They just take the measurement from up there and they put it down here. Everything's fine. And it's like, well, no. One of those things is curved. But turns out both of those things are curved. So the sky mile is definitely inherent on that fact and can't be any other way. So spherical geometry, we went over that. The back end indirect spherical trig you have to use. Reference planes and great circles always being divided in the middle. If you remember the eclipse presentation, we were like, hey, you know how I know it's geocentric? Well, what they do is they use the celestial sphere and they project a planar point through the middle. And from that point, they project shadow based on a series of Besselian elements and interpretive calculations. That's way too much, but that's what they do. That's what it's based on. Oh, I forgot what the point was there. Nah, it's all right. Let's do, this is my celestial sphere thing. This might be the music part. Uh-oh. The celestial sphere. Oh boy, what happened there? It's just a basic, quick celestial sphere demonstration with a little bit of music, right? I think I put this out earlier, but
in the celestial sphere, we'll find our place amidst the stars, endless space. The celestial sphere, we're bound. Everything we know comes from the
Hey, isn't that new band, AI and the Code Breakers?
oh, I didn't know you'd be here. I thought that I was going to get away with this, and I can't actually, in front of a good artist, pretend that this is music. I'm sorry, so.
AI and the DS, you said?
Alan already turned it down.
Yeah, I muted it immediately.
Polaris gleams in the northern sky, a guiding light where dreams fly.
No, it's not necessary. You can just watch me.
Cosmic charm. In the night, it warms the heart.
Right there, that observation is the whole point of the globe argument. They're like, hey, everything on base perspective except the stars, which are like curved and do so because of curvature. Remember that argument? That they're different, but everything else does the one thing, and the stars do the exact same thing for a totally different reason, because globularity. Yeah, that is the basic difference. Right? If the stars obey the same perspective laws as everything else, then there's no basis for calling the Earth a sphere, because that was the crux of their whole argument. Remember, 69 miles per degree is the only thing that proves sphericity. When you ask a glober, when you can see your radius or your planar Earth with your vision radius or your spherical Earth, he was like, no, but I can compute it based on this. I can go right back and say, it's definitely a sphere. Backwards compatible nonsense. Anyway. You can have a fake radius, or you can have a logistic, math-based, cohesive, and logically sound radius application. Your choice. Spreadsheet's available now to everyone. Although Gleam was tearing it up freestyle on Twitter just today, so totally possible. So wait, so how do stars work? Oh, like this. Identically. Oh man, I get it. The Globers just think that this happens because the Earth is curved. We think this happens because logic and reason and every other observation correlate us. This comparison is kind of key, so I do it a couple different ways, a couple different times. That good old celestial sphere. I mean, geocentric plane. I mean, wait, they're the same. It's all the same. Different representations, same thing. I'm gonna let this play only because I love the Æther subscribe thing that I put. It's really hard to make those work, Toby. If you had any more gay clutter, like that thing, I don't know why I like that. But I do, and I inflicted it upon you, and there we go.
Don't forget to like and subscribe.
Please share. Buy my stuff, Patreon Supply, and I have some merch.
Definitely pick up our Æther pockets.
Dude, speaking of my Patriot, does anyone know where I can get some coffee?
Dude, I just got some today from this dude called what is it? Ether Bard or what the hell
is it Brushtail coffee?
Brushtail, that's what it is. Brushtail. It's so I was so happy, dude, and I had like 3 cups right away. It's so delicious. So I'm in a very good mood.
Nice. Thanks for the shout out, y'all.
Yeah,
some of my coffee. I roast it for myself with a special motor setup with a Weber grill. And I sell it online. Go to brushtail.coffee or brushtailcoffee.com.
If you've only drank Dunkin' Donuts like me, then you've never had coffee. Go figure it out. Anyway. So it's crazy.
It goes well with your graticule education.
It goes well with lots of things that are, logical and cohesive and constructive. It doesn't go well with retardation and redundancy and reification of models. And they want to stay away from it with that.
Yeah, you can pick up some Folgers for that.
Ether pockets aren't us, whatever. So this curvature that we are assuming and are using, where does it come from? The basis of our observation, right? We're visiting our longitude presentation from a while back. Where do they derive longitude? Well, they put up a organization, a longitude society. They elected themselves and gave themselves power, used that power to determine that they'd send the whole world on a goose chase to go to the southern extremities to derive the means of longitude to a half a degree and be awarded 800 pounds or whatever that nonsense says from 2014. So they invented the chronometer, the best timepiece ever created by one dude who was challenged by Newton. And before this, the pendulums and ways to compute time had no effect, and the sea was bobbling, and everyone was a fuzzle. And even though they could get everywhere they wanted within a half a degree based on other observations, that doesn't matter. They needed this longitude. So the Royal Society decided they'd send people out there. They go to the southern extremities. They would do what? What would they do? Why do they need to go there? What the hell difference does it make? What is that? So they had to go there and observe the sky and take the star measurements to get the missing angles to map the whole world that they were missing. Nobody goes to the other, all ocean extremities where no land is. How do you map where there's no land? How do you map a place that's mostly water? The sky, the stars, the stars, the sky, the equator, the zodiac, everything in the world is based on the sky. That's why cosmography was all there was until people started to control information. Now you have geography, hydrography, cosmology, cosmography. It's divided and compartmentalized by design, right? If you had it all together, you would see the whole picture. Nobody who controls you wants that. So from your vantage point and your personal perspective and your azimuthal grid, yeah, it's curved. It's a half sphere. Everyone sees that. There's no debating or arguing that. There is a sky that looks a lot like as half a sphere. It reacts that way. It mathematically can be described that way. If you depend on it that way, you will always be right. Coordinate systems that are based on stars are accounting inherently for curvature from the get-go, and then inflicting and carrying that inherent curvature on every subsequent permutation and projection. Because the sky is a spherical surface, first of all, you have what? To make any measurement, you needed a horizon, or a middle meridian, a divider in the middle that will create the biggest circle from which all other circles must be smaller. We're seeing how the longitude convexity problem on the globe Earth has been done, right? They just built this and then told everyone that it was like this, and then having a hard time refuting it since then. They wasted people on the longitude experiment. When they figured that out, they had their mapped the longitude measurements. They could compute what is now the geographic coordinate system. They created that based on the sky. They couldn't do that unless they had mapped the whole sky. What were they doing in the observatory before that in Greenwich for 300 years? Observing the south, the southern sky, the pieces they didn't have. How do you map a observer perspective based southern hemisphere that is tricky, to say the least, without going into two other presentations? How do you map that? Oh, right. Everything is based on the stars. All celestial observations, and it's all the celestial sphere. Can't model a sphere without getting it a sphere. So the fundamental plane principle is what we're talking about. The first requirement for a spherical system. When you're like, oh, we need a great meridian for our planet Earth, you're like, no, incorrect. You need a great meridian and a great circle for a sphere that has a middle that you're bisecting. That is, by definition, the only way. There is only one great circle. There can be only one. If there's another great circle, it ain't a sphere, and you've done it wrong. Everyone getting why the tropics have to be the same size, why the longitude lines are misrepresented, miscategorized, skewed on the shipping channel that Jerms was showing. The coordinate mapping scale is skewed south of the equator, and damn right ridiculous south of the 60th parallel, right? That's kind of what we've been saying forever. We're going to ignore the Antarctic nonsense sun thing for now because I'm so sick of that and it's retarded. So niftily, or interestingly, the way that they've got away with this and the way that we haven't noticed, right, is the distances that we're computing aren't dependent on whether it's a flat Earth or a sphere Earth. It's dependent on which coordinate system we're making the measurements in. Is everyone surprised? Shocking. So nautical miles, statute miles, which are derived from nautical miles in a direct computation, all these measurements based on angles to the stars and not the shape of the ground will remain valid no matter what coordinate system you're interested in. So isn't that interesting? When I read that, I was like, oh man, that's important. That has some gravitas, if you will. So for mapping and navigation, flat or spherical makes zero difference. Zero difference. Why do we argue about that incessantly all the time exclusively? What? Oh, because people don't understand and tell me that Australia is not shaped and therefore flat Earth doesn't exist. And also, have you ever seen a sunset? Stupid flurf, etc. There are 9 people on Twitter who will just be getting this link to this presentation every time they speak forever now. So I hope other people will do the same. Let's spend time and attention where it is deserved. Right. So it's not confusing. It's not absurd. It's basically simple, right? We have a sphere that we see in. They took that sphere as the basis for all measurement. How do you measure a world that is water without land? How do you map the land? You map the sky. Then you worry about the land when you equate it to the sky. Super easy. Counterintuitive, but if you told someone, hey, the celestial sphere has a coordinate system that is a point-for-point match identically translated to the globe Earth, people are like, no, well, no, it has to be that, or you couldn't use either one to navigate, right? If there wasn't a way to have an equivalence there, you wouldn't be able to use the other one. The big point, though, the one that I was trying to spend time on, is for every point on the Earth, right, for this coordinate, there is a unique point in the sky. And then conversely, every point in the sky, based on time at a moment, has an identical spot on the surface of the Earth. Does everyone get that? Anyone struggling with that? Anyone have any questions?
Nope.
I get it. Everybody else good?
You're literally just talking about GP, right? Ground position.
Well, yeah, right. So exactly. And I'm like, hey, if I know the celestial sphere, then I know the Earth. More, if I know, say, one constellation on the zodiac and the time, I know the Earth. But oh, wait. If I know one half of one constellation, say the Big Dipper, then I know the time, the spot, the geographic, the zodiac, the longitude, the latitude, and where everything in the world is. Whoa, stars. Don't look at the stars, guy. Definitely look at the ground. Why don't you look at your feet and mumble for a little bit? Oh, why don't you tell everyone that's not level because topography and see if that helps you? Geographic to celestial, man. So just to prove this is a real thing, I did some math, some chat GPT assisted coordinate transform, some examples, some Cartesian, cylindrical, spherical, all the stuff. It is not only proven, but continuously, consistently proven, continuously verified. Again, starting with sphere, computing in sphere, resulting in sphere. Amazing. So longitude to right ascension is that spherical trig part right here. This is analogous to longitude, but it's measured in time, not in units or degrees. So how do you convert time to degrees? Scaling factor, 1 hour per 15 degrees. Whoa, that sounds familiar. Is that? Oh, that's the crux of everything? The sun's velocity based on its circumference is integral to everything. Good to know. Okay. But we have Earth's rotation and or known as the ether wind over the flat stationary Earth that's never been measured to be in motion by any sort of thing ever test. No measurement or instrument ever in the history of man, but everyone assumes it is. If we just say that that motion and that speed is a component to the coordinate system that you can then increment eyes. Let's say if we take a circle and you take a portion of that circle and then a portion of that portion, you say have a degree or a minute or a circumference. You can take, say, a nautical mile or a circle and say 360 degrees, or you can say 60 miles per degree in sections of 24 would be 900 nautical miles per 24 sections. I think I did that. Or in other words, a circle that is the Gleason's map, that is a longitude line that is exactly 69 miles per degree all the way around the outside.
The equatorial
I don't think we're going to watch this video unless I shortened it. Oh, yeah.
Geographic coordinate system,
It's short.
as both are equator systems. You can imagine overlaying the spherical projection of the sky onto the Earth, aligning the two using the equator.
Yeah, the equator is the comparison point. Without the equator, without that midline, without the comparison, everyone has their own sky. Nobody can tell everyone anything. We're all retarded, wandering around in the darkness, lost underwater. Why would they want this? What is the point? What are they doing? What are they measuring? Well, remember geodesic surveying and super surveying and how they actually measured the Earth? By looking directly at the sky and never measuring the Earth? Everyone remember that? Turns out not only do they relate to the sky, but they directly measure the sky, mark the sky, denote the sky, use the celestial as the geographical, and then when they're off, they do something called deflecting that vertical. What? Yeah. So when you're making a measurement and you're off because you're assuming the sphericity, wherever you're off at, that's obviously a difference in the equipotential geopotential of gravity. That's obviously a little off from the perpendicular requirement necessitated by the definition of a geoid, which of course is the only shape requiring that directionally, definitionally, but no need to worry. When that's wrong, what you do is you look at the sky and then you you look at the ground, and when the sky doesn't match the ground, you just take it and you force it in there and you smush them together hard. And the resultant difference is put in a book called a correction thing. And when people look at the sky and make the same mistake, you'd be like, no, dude, I already got it. I mashed them together. Here's where you'll end up. And you're like, oh, thank you. Good. Now I can navigate. Now I know how the Earth is a sphere. Thank you so much, sir. A little bit.
Hey, nice little ditty about that master plan.
It's so simple and nice and elegant, but the backing for it is maniacal and deceptive and so evil. So Geodesic, dude. I remember when I first came to Twitter, I was like, oh, you want to laugh about maps? How do you determine longitude, and what the hell is an astrogeodetic? And they were like, that's stupid. You made that up. And I'm like, yeah, I'm not talking about maps with you. The whole point of a map is like, what are you projecting again? Oh, a coordinate system. Which coordinate system? The spherical geodesic graticule or longitude lat geographic. Like, how many times you're going to say spherical? We're projecting and starting in this coordinate system, which necessitates, requires, and will ensure sphericity in your components, your calculations, your results, and your variables. Cool. I think I'm going to keep saying that one more time, then we'll get it. So what are they doing? Right. I kind of stumbled upon this backwards when I was looking up surveying. I'm like, oh, you know what, guys, I figured out, you know how they measured the Earth? They looked directly at the sky and did nothing else. What? Oh, yeah. It turns out that's how you always measure the Earth. You look directly opposite up, antipodal, and then you measure that, and then that's how you do it. Like, no. They look at the sky to get like a bearing in the middle of the. No, an astrogeodetic is literally when they're trying to measure that, and they take those points and they force it. The geodesic surveying is riddled with things like ellipsoid, a geoid, and the coordinate systems that they use. They say one is for tides and one is for the Earth, and it's like you're going to simultaneously employ two corresponding different models that both don't work, but you're going to keep both of them all the time, even though, yeah, that makes sense. Or if it's like, say, the sphere of the Earth to the sphere of the geoid, and one's an ellipsoid, because you have Kepler telling you everything is, ellipticity, and of course, with that periodicity, it has to be an ellipse. Turns out, by the way, none of that's true. It's all basic forms of circles, and ellipticity is only necessary when you're Kepler and your harmonic frequency is dependent and you make observations of the past in the sky. So that's where ellipticity comes from. Math, geocentric, heliocentrics need it. We don't, because we're logical and rational and don't try to invert everything we see as an observation into our model. So what do they do? It's the measurement of the deflection of the vertical, the longitude. So again, they did it for latitude and longitude. Shout out to Amish, who threw me a paper that showed me this, that sent me down a whole rabbit hole. What the hell is this? Why are they deflecting a vertical? The geodesic surveying that proves sphericity is based on the same thing that we derive sphericity from in the first place, the sky, the sphere, the graticule, the geographic coordinates. No way. Turns out. Whenever you're wrong, again, you can just take this gravity vector and you can just blame your measurements on the gravitational potential difference on that mountain over there that's pulling your plumb bob, because you don't have a level because your geoid is not perpendicular. So tough when you're taking geodal measurements of level and you can't really tell level because you're constantly in motion, and down is only determined by centripetal velocity around the outside of the sphere, constantly moving, and that's why you need a equipotential downward relationship to know where the hell down is. I know that's a lot, but I think I just verbatim quoted Whitsitt from that first debate. Epic. So this is I think a quick walkthrough, just screenshots of my database where I walked through to take a geographic point, convert that point to a celestial sphere point using all the correct terms and coordinate systems. We're just going to bump through this real quick. We can look through the database later, but essentially we start with the geographic and the celestial. We define the coordinate systems. We note that both of them are using the only thing you have to use to start a coordinate system: a main dividing line and an equator, a great circle, a celestial meridian, etc. The horizon, essentially. You bisect it, you create two equal halves, and off you go. So it turns out, how do you equate them? You start with that basic synonymous fact: prime meridian, the vernal equinox, on the celestial equator, and the actual equator. Those are the points. They are universal, corresponding, and the only way we can relate, again, to any other point. So super easy. That's how you start. And then you start doing the math. Geographic, you get long lat, and you get celestial, like I said, units of time and not degrees. You have this analogous relationship. You do some math. You do the 1 hour equals 15 degrees calculation. You do an offset. You convert it, and off you go. We have these 2 points. That's probably a miss slide here. So we have 1-to-1 correspondence, right? Like I said before, every point is relatable to another point. And there's a unique point for that point in the sky. So prime meridians make that happen. Wouldn't be possible without a bisecting pseudo-scientifical imagined sphere based on a half sphere observation. So the geographic and celestial coordinate system, again, has been defined, been converted, and then now has a 1-for-1 equivalence to right ascension declination. Why 2 spheres with the same coordinates, with the same equidistant comparisons? Well, nobody likes to have just one sphere. When you have a sphere, you got to consistently yield sphere, or why not? You got to measure sphere, compute sphere, and determine sphere. Man, it's a lot. I think we're almost at the end. Here's a couple of different representations of exactly the same thing. A dude in the middle of a plane or a globe, looking around him in a hemisphere of exactly the same distant proportions as every other person in this sign. A bowl, a sphere, a globe. From inside there, you look identical. Not only does it look identical, but the math, a circumference, a radius, an arc, a chord are all the same. Again, it's not that we took a radius and measured a radius. We took a circumference of celestial observations, derived a radius through a simple mathematical formula, and then used that equivalence to literally project everything that we think is there around us. So using that, you can say, actually, the whole world is a sphere, and everywhere that you can't see, it's actually bending perpetually downward. You'll never see it, and everything you see is the opposite, but there's all explanations for that. And if not, then relativity, and also don't be a retarded fuckwit science denier. You gotta believe conformity. With that, arms and weapons, the whole world has believed in nonsense, right? So again, a little bit of meme. Hey, we're gonna find the difference, and you're like, well, this guy's on a sphere, and that used to be a plane, but I guess I had to save it, and it's like, oh, it's the same picture. I get it. We're all on the same page. The circle, dude, degrees, the measurement of a circle. You can bisect a circle. You can quadrisect the circle. You can do degrees, 360, 90, 180, radians, etc. Right? A circle, basic geometry. This is where we're at. This is what we use. This is what they've misinterpreted and incorrectly applied all the way through at every step to get the globe Earth. Circumference is great. Again, there's no spherical circumference. It's just the circumference. Plane Earth is the same. They just took that circumference and they're like, oh, you know what it is? Yeah, we're on a flat plane, but all around us is a sphere, and that's what it's a circumference of. And you're like, oh, cool, mathematically identical. Got it. Here's our dude hanging out in the middle with his radial observation, taking degree measurements that would be indistinguishable from, whoa, this lad on the globe. Did I go too far yet? Then this lad on the globe doing the same thing, right? This guy's over here taking measurements to the sky, thinking he lives on a globe. And this guy's doing the same thing, and together they are indistinguishable, and no one can tell the difference. Although Globers will tell you they absolutely can, though no one's ever seen it, etc. Let's see here. The last part was just a basic coordinate system transform. How this works is you do what's called constant coordinates. So how do you compare things? Well, you take one side and you make it forever in perpetuity, and you measure it. You see how that section? It's perfectly emulating how we started this when we're trying to project that sphere onto all these different shapes. We're trying to shove that circle in that square hole, and we're like, why doesn't it work? Well, here's the deal. We can only do a portion of it, and here we go. So we had the back end to how we started, except this is the math that shows you that it's all the same, that sphere is adequately and accurately represented mathematically in each one of these sections, slices, and representations, right? And the coordinates on the left showing you exactly how that works. So people are like, oh, you can't have it convert cylindrical to azimuthal, and it's like wrong. Absolutely, that's the whole basis for everything. If you don't know that, we can't have a conversation in the first place. Here's a 30-degree slice of a circle or a sphere or the globe Earth, showing you exactly how a circumference is handy. If I say I have a circumference of a circle, the Gleason's map would be that circle. That would be longitude lines that equate to the globe. We have used the same measurement of that circle in circumference to equate that circle to the circle and the sphere to the plane. But interestingly, you can also use an approximation called the zodiac astronomical navigation method, where you just equate your circle to the zodiac. And you say each zodiac has 12, so it has 30 degrees. Each zodiac is 30 degrees of a slice. And instead of using degrees and 1 of a 60th of a 60th of a 360th or whatever, you can just use, oh, well, this one is 30, and we'll use 30 approximations, and we'll go from there. So the same approach as the universe transverse Mercator, when they eliminated the discrepancies by doing local area only, and the big distance that would accentuate the errors would then be cut out to show just, the basic accurate data. And that's just a really cool picture that I definitely meant to use for something else, I think. Hey, let's start comparing this Gleason's map to the flight path on the stupid flight. And no, it's all the same. Stop being retarded. Stop comparing globe to globe to globe and being like, flat Earth is stupid. Or keep doing that and no one will answer you. They'll just link you to this. You can watch it over and over again. Tell us when you're ready. The last part, Tisserats, indicatrix, whatever the hell, is literally how they determined how all these projections are failing to accurately represent the divine sphere. These are all the ways that it doesn't quite get the sphericity of our original starting point. But really, it's just a neat way to show where the maps are being distorted, conformed, and or warped. And of course, if you look at this on the globe, the orthographic starting point, there's no distortions because sphere is sphere is sphere. That's the basic tesseract or how you would work for it. I was trying to use that for something else before I realized I could easily compute distances without doing any of that. My original plan was, hey, haversine gets curve distances. I'll take that curve distance. I'll de-inflate it correspondingly by latitude based on how much it's distorted on this matrix using this math, right? I'll apply it differently at here and here and here, and that way I can get distances. And it's like, oh, that's a good idea. That would work. Turns out you don't need to do that. You can get distances anyway because you're using longitude and latitude, and you can always use haversine to literally determine that mathematically. You can never not do that. So back to the final point here, when we're trying to figure out why do we have maps, cartography, geographic, and we're like, well, we had cosmography. This is where it all kind of starts and ends. They had this, they took it away. They don't want us to know this, essentially. This is my conjecture opinion now, right? This is where I'm going with it. My whole thing has been trying to find out where the globe was inserted, and obviously it wasn't forever, so narrowed it down to 1900, right about end of 1800, right about when Gleason would write in his book, right about after they can correspondingly find newspaper clippings and flat earth everywhere, suspiciously, but it was in schools and newspapers, and then all of a sudden it was nowhere. We've always known globe. Gotta love them fake Greeks. But cosmography is taking everything to account. So the sky, the land, existence. Turns out that's nifty when you're trying to measure land in the land of water. When there's no land, you're like, my method is flawed. So no, don't worry. Turns out we have a star map. And if you look at this map, you can tell, hey, look, it almost looks like the sun translating on a Mercator projection, doing its sinusoidal wave through the path, which, when straightened out, of course, everyone knows is just a circle. It's doing its circle. That's the sun circle. And if we're looking at a star map, we can see, say, not only the sun's path, but we can mark out the zodiac. The zodiac is kind of the original basis for the meridian, celestial equator, comparison point, coordinate transform basis. The zodiac is how you determine the baseline. If you can look at one zodiac, you can get, which 30-degree slice of that circle you're dealing with in the sky, and then you can compute that to the spherical Earth. So if I can look at one star and one band of the tropic of the zodiac, and I can determine from that everything else in the world, I can say that, hey, the stars seem to be important, useful, and probably have some gravitas. So I went on a binge here when I was like, hey, if I can convert maps to any coordinate, can I do a star map? And it's like, oh yeah, absolutely, of course, dude. They're both spherical, so we have at it, could go for it. And here's another one of that same map being projected. The baseline that I'm going for here is, you see this right here. This is the zodiac. These yellow stars are just in the equator and to each tropic and to 6 degrees past each tropic. So if you can't map anything, so you have a meridian or a middle or a bisecting, and then you know that the stars have this bisecting portion, couldn't you just take that observation and base everything else on that? Get tropics, get an equator, get a circle, use that circumference, and could literally create the world we live in today? Or is that just me? Let's try this. If we look at it together, right, we got orthographic globe Earth on the right, azimuthal flat Earth on the left, zodiac being displayed prominently in the middle. You see how that bisecting sphere, look at that prime meridian, looks like it's right on the great circle, the big important spot you need to focus on. That's where the zodiac is. So if I could see like one arm of the Big Dipper, I could tell you where Australia is and how distant it is from me. It's a lot of work to get there, but that is what I'm saying. You could say, hey, nautical mile based on that observation converted back to my right ascension declination to my longitude gives me a corresponding spherical geodesic distance of glob. Turns out, no way. Whew, went a little over, but that's pretty much it. Did I spell thank you right? Yeah, right. Oh, man, I don't know what that is. That's probably unrelated. I don't know. So, questions, comments? What else we got? Let's check my itinerary. What did I forget?
Very nice. It turns out when you assume sphericity, you'll find sphericity.
If you start with a sphere and you calculate within that sphere and then you get results, they weirdly are spherical. Yeah, but that's flat Earth proof for flat Earth is stupid or math or something. Oh, I think I have a spreadsheet to go through. We can do some Haversine calculations. We can show you how to make a spreadsheet that will compute Haversine equivalents, how you can, use the coordinate system that they beat us over the head with as a neat tool to dance circles around them mathematically, logistically, critically, and whatever we do as flat earthers do. What did I forget? Nope. Astrogeodesic, sphere, cosmography. That's pretty much it.
Nice. Very, very, very nice. A lot of great visuals, man.
A lot of custom visuals, man. Canva's the shit.
Yeah, nice job.
Nice. Thanks, man. So, did you handle the AI music? Did I make up for it with the other stuff, or did I ruin it with that?
It was minimal besmirching.
Nice. I did it anyway.
So if someone were to ask
Besmirched
you, why can't you make your own flat Earth map? What would you say?
So I would say I can make the map that they made only because we're basing it on the sky, and my sky is the same as your sky. I can only use the spherical sky that I see to make maps, and I can definitely recreate the spherical map that I see based on my observations to the stars alone. But unless the stars were planar, I can't create a planar map the same way. Does that make sense? I've recently refined that response, I think.
I like that response.
So you're going to be making geodesic arcs to get distances as well on a flat Earth map because the sky is curved?
Well, what I can do is consistently get that distance x that everyone always gets based on the stars. I can do that independently of any of their stuff. I can look at the sky and I can tell you nautical mile, geographic distance, spherical trig, and right such declination coordinates for where that is on the Earth. Right? I can do that, but I can't do anything else. That's why they did it. Now I can recreate that, and that's it. And now we see why we're in this predicament. Why can't you just make a map? And it's like, well, maps are the sky, and the sky is a sphere. So unless you have a flat sky that I can use, we're flat out of luck, dude.
Like it.
Damn, it's a lot. But yeah, that's kind of relevatory, instrumental, and necessary. So flat earthers, stop arguing things we don't want to defend. And Globers, educate yourself. Stop being retards. I'm sure you're not listening at this point. I'll be sure to link you here over and over again.
Yeah, I linked this presentation 3 times while you were giving it. So
There's going to be 12 people making the remedial comments we started with, and I'll just be like, oh, not only ignored, properly refuted, destroyed, and still moving over here.
Very nice. Very, very nice. I like the way you summed it up at the end there. That's pretty much the crux of it.
A lot of thought, a lot of work, a lot of working out, a lot of different components, man. If I didn't go through like geodesic, like surveying, then longitude, then coordinates, and then I wouldn't have connected any of those dots. I remember when I was doing geodesic, and I'm like, guys, they're looking at the stars for a weird reason or whatever. It turns out they're not measuring the Earth, because this thing they said it was proving the Earth was a sphere. They just measured the sky. That's enough for me to stop looking into it and say this is retarded. But really, it's like, oh no, you should go further. That's the basis for everything. Not only is that for the sky, it's the satellites, the geodesic, the coordinate, the WGS-84, every survey ever taken, literally every geodesic survey out there, every compartmental, every measurement that they have to, say throw out if it doesn't match that radius, etc. All based on this. So curvature in the sky gives us nothing, not a globe Earth. You just got to understand the sky it's a half sphere, and you don't see forever because you're not Superman.
Excellent. Well, cool. Anyone else? Any final thoughts? And Shane, anything else you want to tack on before we wrap up streams here?
There's one more example that I just thought of that I already forgot. Let's maybe I'll remember in the next 4 seconds.
3, 2, 1, and we're gone.
And
Cool.
it's gone.
All right, then. Let's close streams out. Thank you, everyone, for listening. And, Shane, thanks again for putting all that time in. Thanks for the great visuals. It was very thorough, and we very much appreciate that. Hopefully, we can all kind of get this straight now. Like Shane said, don't argue things that we're not going to back you up on. I mean, obviously, argue whatever you believe in, argue, whatever you find to be true, objectively in your life, whatever your own burden of proof, and investigate things objectively. But at the same time, what Shane has just laid out here is just the facts of it. We're talking about the sky, and the sky observations appear to be quite accurate, given the maps that we have, but it's all based on the spherical observations of the sky. So, yeah, Globers, you're right. It appears that when we map the ground to the sky, it looks kind of like a globe, because it's mapped to the global sky, to the spherical sky. And flat earthers, like, that is what it is. And so, don't run from that. It's just, but it just understand that, that's what we're looking at. It's just a map of our vision of the sky. So, yeah.
We're all looking at the stars. Everything that's on the map is actually just the stars. If you look at maps of the 1700s, actually only from 1701 to 1799, suspiciously, all the maps were in this double orthographic 2-hemispherical display, which is exactly as you would display a star map for a northern and southern hemisphere. Or say if you bisected your sphere with your Great Meridian and then put it in a coordinate system, that's exactly how you would do it. Right? But a good last thing, a good example for knowing how how observations based on the sky doesn't work for forever in perpetuity linearly. You can ask ChatGPT to give you a distance based on 85 degrees. If I take a measurement, how many miles is it between latitudes? And it's like, oh, immediately it will do like radians, cosines. It'll backwards compatible compute that geographic determined distance right back into you, and you're like, I got it. It proves the Earth, and it's always this. And it's like, no. Use it based on a sextant site, your observation only, and then use trigonometry to tell me what the distance is. And it's like, well, no, can't, doesn't really work. It's not fair. Doesn't, hey, it's not close enough. It's like, okay. So it's not linear, or you tell me that it can be linear sometimes and linear not. Do you know what linear is? And it's like, upon further examination, it turns out that I can't in good faith say it's linear because it doesn't work at every step as necessitated by something that is linear. So it's like exceptions are made, and it's nonsense, but you definitely see forever, and it's linear. It concludes, and you're like, okay.
And just to clarify on that, what they have got us, or what they have convinced us of, at least prior to us starting to question these things, is that essentially that you just see infinitely in all directions. Your hemisphere of vision that Shane's been describing this whole time, they claim that those stars that you see just over the horizon there, that those are just, equally as far, relatively equally as far as the ones directly above you. But then in that case, that relationship as you go up to your zenith, along your azimuth from the horizon, that relationship of where those stars are should be linear. It shouldn't change. And it turns out with celestial navigation, my understanding is that it's not actually linear, especially once you start getting down towards the horizon. And so, that implies, especially if, the logarithmic function that it seems to apply there, that implies that you're peaking down into that exponential point where the planes are converging, exactly like you would expect with two parallel planes.
Right. So they need that linear thing to be linear because that's how the basis for, like, say, light speed, light distances, that's the standard candle, the geographic, like the solar system, the observation of 0.53 degrees sun that computes a size, diameter, and distance all concurrently. But, all of that is based on it. Exactly. So if it's not linear, then all of that isn't true. And what happens is they take something that's almost linear and then restrict you to the linear portion and then give you a correction table for when it's not linear so that you will continue thinking it's linear. Why would they do all that? Knowing that the apparent angle to apparent height based on what you see is always going to be this tapering off limit, especially if you accurately define, say, the trig you're using with a unit circle governing the radius as the hypotenuse to make sure your vision radius doesn't stray from 3959 to accurately measure reality. Then you see that towards the extremities, it doesn't math out correctly, right? Unless you do offsets and radians calculations to get the missing component mathematically back into your geodesic, which you can always do. But if you use optics and the way that you see, which is what you're supposed to do, it shows you quite plainly, this is how it is, this is how we've been tricked, and this is why it's important. I think that's a good way to end it.
Excellent. Cool. All right. Well, everyone, check us out on Thursday night for our Twitter space, Flat Earth on Thursday night. And we'll just be chatting about meta arguments. Where me, Shane, and Alan are all going to bring some of the things we've talked about recently. Shane's going to talk about sky optics. Alan's going to talk about general relativity. And I believe I'm going to talk about geodynamo and the core a bit. And we're just going to kind of lay out a few, like 4 or 5 points each about some meta arguments. So check us out for that. And yeah.
Is it like more like distilling these complicated big presentations into a
Yes.
15-minute like
Yes.
perfect emulated package that we can share, disseminate, and which is what we got to do for this to be shareable? And Alan had a great idea, so I'm going to make this presentation into a 15-minute version that you can take away with, and then Alan will do all of relativity the same way, and Toby will definitely create the best model that they don't have, showing you the geodynamo in 15 minutes. Nailed it.
So yeah, and then yeah, if you didn't hear, we're changed our schedule up. Reading night is now on Monday nights. And then, of course, we'll still be doing roundtables, Æther roundtables on Tuesday nights. And then on Thursday night, we'll be doing our X Live Twitter Spaces. So check that out. And I believe, I don't know if there will be a Flat Earth Fridays, but there might be some people around for that. So check that out. And yeah, everyone, take care.